Welcome back, dear students, to the Tetrahedron chemistry classes. So in the combined spectral problem series, today I am going to solve a new problem which I have taken from the spectroscopy book by Pavia, Lampman and Kriz. And this is the problem number 20 of your chapter 3. Okay, since this problem is purely based on the NMR spectroscopy, so I have changed the title here, NMR problem based on the isomers. Okay, so what is the question? Following are the NMR spectra. Only one is shown here. Rest two are present on the different slides. Okay. So following are the NMR spectra of these three isomeric esters with the formula of C7H14O2, all derived from the propanoic acid. Provide a structure for each of the following. So first of all, you should know your propanoic acid is what? CH3, CH2, COOH. This is your propanoic acid, and from this propanoic acid you have derived esters which have the formula of C7H14O2. Okay, here you can see 1, 2, 3. Only 3 carbons are there. It simply means your 4 carbons are present in the different part which is connected with the oxygen. So how we can make a ester for this? Say this is your CH3, this is CH2, and this is C double bond O, and then your O. And then you are having rest of the things. Only 5 hydrogens so far you have written, and here 14 hydrogens are there. So you need to adjust these 14 hydrogens along with the 4 carbons, because you have written only 3 carbons. So what we can do, we can simply write an ester for this one, which will look like CH2, 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 and CH3. So your carbons are 1, 2, 3, 4, 5, 6, 7. 7 carbons, 3 to 5 to 7 to 9 to 11, 3, 14. 14 hydrogens and 2 oxygens, right? So first ester you can write in this way. Then what are the other esters which you can write for this one? The second ester for this one you can write only by adjusting this alkyl part, this butyl part you can adjust. First of all, this is your normal butyl, okay? And then you may write your another structure. This would be your CH3, this is CH2, this is C double bond O, this is O, and then you can write your next structure, which will be your, say, CH2, CH, and CH3, and you can give one branch over there. This is basically isobutyl propanoate, okay? And the third year could be CH3, CH2, C double bond O, O, C, and then 3CH3, CH3 and CH3. Okay. So what are these compounds? So last compound is your tertiary butyl iso, and the earlier one was your simply butyl propanoate. Butyl, or simply you can write N-butyl. N-butyl propanoate. So this is how you can write this particular structure. Now, since you are having only the 3 possibility of different structures, you can go for their proton NMR spectrum and their their splitting pattern as well. So first of all, I am doing for, say, this particular compound, the last one, tertiary butyl. So if you are looking for the splitting pattern of this particular hydrogens, 3 hydrogens, these particular hydrogen, 3 hydrogens, so you will apply n plus 1 rule, n plus 1, where n is the number of hydrogens present on the neighboring carbon, and the number of these hydrogens are 2. So you can write 2 plus 1, that will give you 3. 3 means triplet. So it will produce a triplet. So you can simply write a triplet is produced here. Now, if you want to calculate the splitting pattern of these 2 hydrogens, so you need to look the hydrogens on the neighboring carbon, which are 3 in numbers. So again, if you apply the n plus 1, so this will give you 3 plus 1 equals to 4. 4 means it is quadrate. So this will produce a quadrate. And now you can see chemically the environment of all these three methyl groups are same, so they all are equivalent, and in this particular carbon there is no single hydrogen present on it, so there will be no splitting of any of these identical methyl groups, so they all are same and the identical, basically they are isochronous, so they will produce only one peak, which will be your singlet. Okay, so this is tertiary butyl propanoate. So if I look my spectrums, so this spectrum is quite typical: doublet, quadrate, multiplet, triplet. So this is not actually exactly looking like this particular one. So what I can do, I can move to the next one, right? Say this is quadrate, this is triplet, and this is singlet. So this is actually looking like your this which I have drawn here. So this is basically your compound B. If I check, yes, this is your compound B. So I can write this as compound B. Right. So this is your compound, and then we can decide the chemical shift as well. So this quadrate is somewhere around 2.1 ppm. Quadrate is resonating at 2.1 ppm. So I'm writing 2.1 ppm for this one. And this is quite obvious because this carbon is directly connected with this electron withdrawing carbonyl group. So definitely it will be little bit downfield. Okay. And then you are having this particular singlet. So singlet is due to this one because they are directly connected with the carbon but not to the any electronegative group. But again, you can see this oxygen is basically what? This is electronegative in nature. So this the effect of the electronegativity will go to these onto these methyl groups. So deshielding will take place. So second deshielding will be there for this. Then the deshielding will be there for these three methyl groups. So second most downfield signal is this singlet, which is this one, and this singlet is resonating somewhere around at 1.3 ppm. 1.3 ppm. Okay, you can argue that this oxygen is more electronegative in nature than this particular carbonyl group, then this signal must be more downfield than this one, but this is not true because this oxygen is not directly connected with these three hydrogens. Okay, and the effect of the electronegativity decreases, right? That's why the deshielding is little bit on the lower side, that's why it is appearing at 1.3 ppm. And then you left with this CH3, which is far away from this less electron withdrawing carbonyl group. So this will be most upfield, this triplet, and it will resonate somewhere around 1.1 ppm. Okay, so this is how you can solve this particular problem. Now moving to the next one, here only quintet is written here and only sextet is written there, but all other peaks 1, 2, 3 and 4 other peaks are also there, and you can see the resolution of the peaks are not very good because I have taken the screenshot, and in the original book itself it is not that clear. So you need to understand what are the different multiplicities of these other peaks. So I am telling you the multiplicity of other peaks are basically this is again your triplet if you closely look to this one. Okay, and that one is your quadrate, and after quadrate you are having another triplet and then your another triplet. So basically your molecule is having 1, 2, 3 triplet, one quadrate, one quintet and one sextet. So how we can get these things? Okay, my structure was CH3, but if you see this one, so this methyl group and this methyl group, they are same. Okay, when they are same, that means they will produce one peak, and in their vicinity there is only one hydrogen. So this will produce doublet, this will give you the doublet. But in your spectrum there is not a presence of any doublet. When doublet is not there, that means this spectra is not actually relating with this particular structure. So what I can do, I can change this structure a little bit. So this will produce a triplet. As I already told you, how you will apply the n+1 rule, where n are the number of the neighboring hydrogens, which are 2 in this case. So you'll write 2 plus 1, that will give you 3. 3 means triplet. Quite fine. And this will produce a quadrate. This is a typical splitting pattern, quadrate. If you apply the n+1 rule, 3 plus 1, 4, that means it will produce a quadrate, like in the earlier slide I have explained to you. So this quadrate you have also explained, this quadrate. Okay. And then moving here, you are you are looking for the splitting pattern of these three hydrogens. So in the neighbor you are having only two hydrogens. If you apply the n+1 rule again here, this is n+1, this will give you what? 2 plus 1, this will give you the triplet. So again a triplet is here. And now you can see here, if you want to calculate the splitting pattern of these hydrogens, so in the left hand side you are having two hydrogen, in the right hand side you are having three hydrogens, and all are the alkyl hydrogens. So there is not much difference between their what you can say, the coupling constant. So you can simply apply the n+1 rule to this for this particular one. So if you apply the n+1 rule, so what will happen? So I'm writing n+1, where n are the number of neighboring hydrogens, which are 5 in this case. 5 plus 1 equals to 6. 6 means it is sextate. Okay. Sextate means 6. 1, 2, 3, 4, 5, and 6. This is your sextate. So this sextate is here actually. Okay. And then you can go for this one. These two hydrogens are here. And if you want to calculate the splitting pattern of this for these hydrogens, so 2 on the left hand side, 2 on the right hand side. If you apply the n+1 rule for these, so what will happen? n+1 means number of naming hydrogens, which are 4. 4 plus 1 equals to 5. And 5 means it is quinted. It is quinted. Okay. So you have justified this quinted as well. So 1, 2, 3, 4, and 5. So this quinted you have justified. And then if you look for this one, again it will produce a triplet. 1, 2, and 3. Why triplet? Because there are no hydrogens present on the left carbon, but right carbon is having two hydrogens. So 2 plus 1 equals to 3, like this one. So this will produce a triplet. So you are having how many triplets? One triplet here, two triplet here, right? And your third triplet, and 1, 2, 3. Three triplets are there. And one sextate, which is this one, and then quintet, which is this one. And then you can very easily apply the n+1 rule here. So what I missed here, please note that oxygen I have missed. Okay. And now this triplet will be most downfield because this is directly connected with this particular oxygen. So basically this signal is this one. Okay. And then you can see next one is your quadrate, which is this one. Quadrate is connected with this carbonyl oxygen. So this will be second downfield signal. So for this, the peak is this one, this quadrate. Okay. And then you can analyze by your own which peak belongs to which one. This is farthest from this electronegative oxygen. Up to 4, after 4 carbon, the CH3 is present. So this triplet is most upfield. So if you want, then you can write this triplet as this one, right? And then you can go for your, say this was your quintet. Quintet is this one, right? And your sextate is this one. Clear? And then you left with the last triplet, which is this one. So this structure, this particular compound, this structure of this ester is basically relating with this particular spectrum. Now, if I move further, and then this one is your A. Okay. So for this A, again, I can write the structure. Now, again, this is quite simple. This will produce a triplet, as I have already explained to you. This will produce a quadrate, as I have already explained, right? And now if you look for these two, right? These two methyl groups are equivalent and they will produce a doublet. Okay. And you see this hydrogen, which is having on the left hand side your 2 of hydrogen, here your 6 hydrogen. So typical splitting will occur and they will have the different value of the coupling constant because oxygen is here. So you will get a multiplet for this particular hydrogen. Okay, you will get a multiplet for this particular hydrogen. So 1, 2, 3, 4, 5, 6 and kind of a multiplet. Okay. And then you left with this one. This will produce a again a doublet here. So you see this one doublet, which is this one, not this one, right? Because it is connected with the oxygen directly. So this doublet is basically belongs to this one, resonating at somewhere around 3.9 ppm. So if you want, then you can write 3.9 ppm for this one. Okay. And then you are having this particular quadrate. So this quadrate is basically is this one. Okay. Because it is connected with the electronegative carbonyl group, right? And then you are having this multiplet, of course, this one for this one. And then you are having a doublet, very upfield for this one. Okay. And you left with this particular triplet, and that triplet belongs to this particular structure. Okay. So these problems are these kinds of the problems are very easy if you want to solve these problems logically. Say the very important observation already given in the question is they are the isomers of the propanoic acid, ester isomers of the propanoic acid. So you need to write the propanoic acid and then make the esters for them, and then write the different isomers for this one. Then you will be able to solve such kind of the problem. I am going to solve yet another problem from the spectroscopy book by Pavia, Lampman and Kriz, and this is the problem number 21 of chapter 3, which is given in the exercise. And it's quite a simple problem and elementary problem. It will not take too much of the time. So first of all, what we will do, we'll read the question. So see, the title should not be your combined spectral problem, because this problem is purely based on the proton NMR spectrum. Okay, but since I am dealing with the combined spectral problem, so I have decided to put this particular problem in this section. So I have given this name, combined spectral problem. Okay. The two isomeric carboxylic acids that give the following NMR spectra 1 and 2, both having the formula C3H5ClO2. Draw their structures, most probable structure. The only thing given in the question is the C3H5 and your ClO2. And it is already given in the question that this compound is carboxylic. These compounds are carboxylic acids. So that means one thing is sure, both are having COOH group, this functionality, COOH. This is offset 1.7 picometer, ppm, parts per million. Okay. So this NMR scale is extending from 0 to 10 ppm, and this peak, which is offset by 1.7 ppm, that means it is resonating at 11.7 ppm, and you know, in the range of the 10 to 12. Please remember, in the range of the 10 to 12 parts per million, you always have signal of the hydrogen which is connected with the COO. Okay, so it is quite clear. This is your 11.7, right, for compound A. And in the next isomer, the peak is offset by 2.2. Again, the scale is extended from 0 to 10 ppm, and it is offset by 2.2 ppm. That means the second compound is giving this peak for this hydrogen at 12.2 parts per million. Okay, this thing is quite clear. Now, if you see this particular first spectrum, two triplets are given here and nothing is there in the spectrum, only two triplets here for the compound A. So how we can get the two triplets? This I have already told you. When your CH2 is connected with the CH2, so this will produce a triplet, and this will also produce a triplet. And for the beginners who are watching this video for the first time, the splitting pattern is N plus 1. That means if you want to decide the splitting pattern of these two hydrogen, you need to check the presence of the hydrogen in the vicinal carbon. So this carbon, the carbon is the vicinal carbon, and it is having two hydrogen. To check the splitting pattern of this CH2, we need to identify these two hydrogen as N. So you can write 2 here, 2 plus 1, that is 3. 3, it stands for the triplet, that's why this triplet is here. And same is true for this one as well. Trying to identify the splitting of these two hydrogens. So you need to check the hydrogens present on the vicinal carbon. The number is 2 again. You have confirmed the presence of COOH, and you have confirmed the CH2, and your formula is nothing but. So if you connect these two fragments, this is fragment number 1, This is fragment number 2. If you connect these two fragments, you are having CH2, CH2, COOH. This will give you a singlet at 11.7 ppm. This will produce a triplet, and this will also produce a triplet. Okay. Now you left with the chlorine. The only possible way is to put chlorine here. There is no other way. Now you need to decide the chemical shift of these. So here you can see, if I go back, this triplet is a little bit downfield and this triplet is little bit upfield, and you need to decide which one is the upfield and which one is the downfield signal. This is somewhere at 3.8 ppm, right? Downfield signal is at 3.8 ppm. 3.8 ppm of chemical shift to this one. Okay. And for this one, I can give 2.8 ppm. So these two signals are there, 3.8 and 2.8. So this is looking like the more correct structure for the compound A. The only question is that this chlorine actually, which is electronegative and as well as the electron pushing. So its electronegativity dominates and it will suck the electron density towards itself, making these hydrogens de-shielded. And you know, de-shielded hydrogens appears downfield. Downfield means higher value in ppm for the chemical shift. So this is your first compound. Okay. And now you can go for the second compound. This is a doublet here and a quartet. Doublet and quartet and one COH group. So acid is confirmed, one doublet is confirmed and another quartet is confirmed. Only possible way to get the doublet and the quartet is this particular kind of the bonding. Okay. So this will produce a doublet, which is this one, and this will produce a quartet, which is this one. Now you know, if you want to decide the splitting pattern of these three hydrogens, you need to check the hydrogens on the vicinal carbon. This is vicinal carbon having only one hydrogen. If you apply the n plus 1 rule, so you will put n plus 1 here. So 1 plus 1 equals to 2, and 2 means doublet. That's why this doublet is here. And if you are deciding the splitting pattern of this hydrogen, you need to check the hydrogens present on the vicinal carbon, which are 3 in this case. So if you apply the n plus 1 rule, n plus 1, that will give you 3 plus 1, that is 4. 4 means quartet. Okay. So this quartet is there. So you are having the fragments COOH and another fragment is CH and then CH3. The only way by which you can attach a chlorine to the system is on the second carbon. So this is the most probable structure. And now you can see here, this particular signal, this will appear somewhere 12.2 ppm. So if I go back, why this signal is actually at 12.2 ppm, while for the earlier one, the signal was around at 11.7 ppm. So the reason is quite obvious. This hydrogen is connected with the carbon which is having the chlorine. So this chlorine will also de-shield this particular hydrogen, and due to the de-shielding, it will appear little more downfield at 12.2 ppm, while in the earlier case, the chlorine is on the second carbon. It is far away from this particular hydrogen, so de-shielding effect is low. That's why it was appearing at 11.7 ppm. But in this present problem, it is on the second carbon. It de-shield this hydrogen, so that's why it will appear on the 12.2 ppm. Now the chemical shift for this particular hydrogen, it is only one hydrogen connected with the electron withdrawing chlorine. So this quartet will be quite downfield. So I'm writing Q this one, and this Q will appear somewhere around at 4.2 ppm. Go back and check the value. Yes, you can see here this quartet is appearing exactly at the position I have given here, 4.2 ppm, and your next signal, which is nothing but a doublet, I'm writing D for this one, it is appearing at 1.8 ppm. Okay. So this is how your proton NMR spectrum is useful in differentiating the two different isomers. The following compound with the molecular formula C8H11N shows a doublet at about 3350 centimeter inverse, and bands in the range of from 1600 to 1450 centimeter inverse in the IR spectrum, and draw its structure. Okay, and this is the proton NMR spectrum. And this, if you carefully look this proton NMR spectrum, then you can quickly jump up to the conclusion that this molecule is having a benzene ring. Why? Because we are having a multiplet kind of the signal resonating at near about 7.1 ppm, which is clear cut indication for the presence of the benzene, right? And then you are having the pair of a triplet. Two triplets are given here in the range between 2 to 3, more precisely somewhere at 2.6 and 2.8, right? And then you are having this particular singlet. Okay, and if you read the information given in the IR spectrum, which is doublet at 3350 centimeter inverse. So the student who knows the interpretation of the IR spectrum, they may quickly jump up to the conclusion why this doublet is here. But if you don't know, don't worry, I'll come to this point a little later on. Okay, and then there are the ranges of bands from 1600 to 1450 centimeter inverse, which is, you know, due to the presence of the double bonds of the benzene ring. Okay, and you need to draw the structure, most probable structure for this particular compound. So as my usual practice, what I will do, first of all, I'll calculate the hydrogen deficiency index, because this compound is containing nitrogen. So I have expanded this particular formula in my earlier classes where only hydrocarbons or the oxygenated hydrocarbons were there. In those cases, I have used the little compressed formula where I didn't include the nitrogen and the halogen in the formula, but here I am including the nitrogen as well as the halogen. So how we can calculate 2, which is a constant, and number of carbons given in the question is 8, right? So it is better to write C8H11N. Okay, and then plus 2 is there, and one nitrogen is there, so you will add 1 to it, right? And then minus 11 minus 0, right? And then you will divide it by 2 according to the formula. So what you will get, 8 to the 16 to 18 and 19. This is 19 minus 11, okay, divided by 2. This will give you simply your 8 by 2 equals to 4, right? So hydrogen deficiency index is 4, and this is the perfect fit for the benzene. So these are the 3 double bonds and 1 ring. Okay, so this is perfect fit for the hydrogen deficiency index of 4 actually. Okay, so what is the meaning of the 4? Your molecules may have 4 rings, which is not possible in this case. Your molecules may have 4 double bonds, which is again not possible in this case. Okay, why I am saying that this is not possible? Because I am having the information from the proton NMR spectrum, benzene is there, so there is no probability of the 4 double bonds. So what other options are? Other options are uh, 1 ring plus 3 double bonds. This is the perfect fit for the benzene, which is also confirming from this proton NMR spectrum. So first of all, this thing is quite clear that benzene is there. Now what you can see, because you are having the nitrogen, so there may be the presence of 2 different kinds of the functionality here. First is your carbon triple bond nitrogen, okay, and second is NH2, right? And for the beginners, this may be the great confusion for them. Okay, but if you know the IR spectrum and the concept of the hydrogen deficiency index, so based on this, you can quickly discard the possibility of the CN ring. Why? If along with the benzene ring, CN is also there, then the hydrogen deficiency index must be 6 or the 7 for this one, right? 6 or 7, you can calculate it, but it is only 4 here, right? So that means this cyanide is not there. And one more very important thing is that if cyanide, say if cyanide was present in this particular compound, then definitely we would have we would have the band in the IR spectrum which will resonate somewhere around 20 to 60. So this is the range for the cyanide, 2260 to 2210 centimeter inverse, right? But this band is not there in the IR spectrum, because in the IR spectrum we are having the band at 3350 centimeter inverse, and between the 1600 to 1450 centimeter inverse, and the information about the cyanide is missing in the IR spectrum, so we can discard this particular thing. Okay, so now you are having the two fragments. First fragment is benzene ring, and second fragment is the NH2 group, right? So this is the most probable. In a little while, we will also confirm why this NH2 is there. Some other informations are also there, right? And then you can see here, two triplets are there. 1 and 2, two triplets are there. So how we can get the two triplets? The only possible way is that my CH2, if connected with the another CH2, so this will give you the triplet. If you want to calculate the splitting pattern for the this methylene, or these two hydrogens rather, right, then you will apply the n+1 rule. So according to the n+1 rule, what will happen here? N is the number of neighboring hydrogens, which are 2 in this case. So what you will do, you will put 2 here and +1, that will give you 3. So this will produce a triplet in the proton NMR spectrum. And this triplet and this triplet is there in the proton NMR spectrum. And similarly, if you want to calculate for this these two hydrogens, so again in the neighbor, two hydrogens are there. So for this again you will apply the n+1 rule. Okay, for beginners I am writing it again, right? So again it will be 2 + 1 = 3. So you are getting the two triplets. Okay, so second fragment is this one. Okay, this is fragment number 3. So in short, you are having these three fragments. And if you count the total number of carbon atom, 6, 7, 8. So this is C8, 11 of your hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because this will be mono-substituted, you will have only 5 hydrogens on the benzene ring, right? And so you are having these three things. And now you can conclude your structure, what actually we are having. So if I put the pieces together, I'll have this thing. We left with the interpretation of the IR spectrum. So here you are getting a doublet at 3350 centimeter inverse. So why we are getting doublet at 3350 centimeter inverse, right? Because you see this NH2 group is there. So this NH2 will produce a doublet like your molar teeth, kind of W actually. Okay, so this doublet is due to the presence of the symmetric and asymmetric stretch of NH bond. Okay, so this signal basically which we are getting at 3350 centimeter inverse is due to the presence of symmetric, I am writing, I have confirmed this thing, and the resonating range in the IR spectrum of the NH bond is same as your OH, and it is at 3350 centimeter inverse. So this will resonate at 3350 centimeter inverse. And you are having this particular bands in the range of the 1600 to 450 centimeter inverse, which is due to the presence of the double bond present in it, right? It is very, very important. So you are having this, you are having a CH2, and then you are having this CH2. Okay, so this confirms this thing, right? So the most probable structure for this particular compound is this one. But you left with the, so you have explained this, you have explained these two, but you left with this singlet. Why this singlet is there? This is something very, very important, which you need to explain. Obviously, this singlet may be due to the presence of the NH2 group, right? And this is very, very important. The NH2 group in the proton NMR spectrum, basically the amine protons, they generally gives a broad singlet. However, this singlet is not very, very broad, but this NH2 gives a broad singlet, 1.2 ppm. 1.2 ppm. If you carefully look this is resonating at 1.2 ppm. And this was giving triplet. This is also giving a triplet. And this will give a singlet. And the chemical shift, generally the chemical shift of the NH proton is roughly 1.2 ppm. And you know the different hydrogens are present on the benzene rings as well. So these two hydrogens are of the same kind. In the previous classes, I have explained this thing. Okay. So you see this hydrogen and this hydrogen, they are the same because they are having the same environment. Here you can see at this position, no other hydrogens are there. And in the bottom positions, you are having two hydrogens. So these two have the same kind of the environment. And based on the same argument, these are the different kind of the hydrogens which are equivalent with each other but different from the HA, because the environment of these two hydrogens is hydrogen on the bottom and two hydrogen on the top, right? So these are the different hydrogens, and this is your third set of the hydrogen. The environment of this hydrogen is only two. So these three groups are forming on the benzene ring, and this is the very common pattern of the mono substituted benzene. So the signal which you are getting at 7.1 ppm is due to these hydrogens. So you are getting at 7.1 ppm. Now you can see, if I go back, you are having two triplets here. One triplet at say 3.6 and second one is 3.8. The signal at 3.6 ppm, and this signal that is triplet at 3.8 ppm. This signal will obviously be little bit upfield because this NH2 group is there, and this NH2 is electron pushing group, right? So it will push the electron onto this particular carbon atom and shield these hydrogens. So due to shielding, these hydrogens will be little upfield, while these two will resonate little downfield, because the circulating electron cloud will not shield these hydrogens much more strongly. This singlet, this is due to the NH. So you can say the two hydrogens are there. So please remember, it is very important. The signal is very broad due to the rapid exchange or the quadruple broadening from the nitrogen atom. So this is the most probable structure for this particular compound. I hope you understood the problem. Okay. Now moving to the next problem. This is the problem number 22, and what it is saying: the following NMR spectra are monosubstituted aromatic hydrocarbons. So it is also it is already given in the question. It is monosubstituted aromatic hydrocarbons. That means this molecule is having the benzene ring and the carbon and the hydrogen with the formula of C10H11, which is given for this question. So there is no need to interpret this one, but I'll interpret this as well, right, for the beginners. So simply the problem is saying it is the aromatic hydrocarbon, and this proton NMR spectrum is given, and you need to interpret this one. What information is there? This triplet is given, and then this doublet is there, and then quintet is there, and then sextet is there, and these are the benzene ring protons. So immediately what you can do, you can write this benzene ring. Okay, and then different fragments which confirm this splitting pattern. Here you can see this is having the sextate. So how we can get the sextate? Say this is CH connected with the CH3, okay, and connected with the CH2. It is quite clear. You see here, three hydrogens are here, two hydrogens are here. If you want to calculate the splitting for this one, so you will apply the n+1 rule, n+1. So in the neighbor you are having 5 protons plus 1 equals to 6. So this will give you sextate. So now what you can do, you can decide the splitting pattern of this one as well as this one. So for this one, definitely you will get a doublet, because in the neighbor you are having only one proton. So you'll write n+1. It's simply 1 plus 1 equals to 2. So it's a doublet. And one thing is sure, since this is producing a sextate, only CH3 and CH2 would be possible on the left and the right hand side, and there is no other substitution of the carbon atom on this particular carbon which is having the hydrogen again. So the pattern, you may conclude the benzene ring which is connected with the CH, and here this is your CH3 and this is CH2. Now it is quite clear this will produce a sextate due to the splitting by these 3 and 2 protons, which I have explained here, and there is no hydrogen attached to this benzene ring. So basically this kind of substitution on the benzene ring is there. So this is producing sextate and this is producing a doublet. What you left with the quintet? Quintet means 5 splitting pattern of 5 different peaks. So how we can get the quintet? So for quintet, what we can do, we can put say CH3 here. Okay, so if I put CH3 here, you see, you are calculating for these two. So 3 hydrogens are here, or 1 hydrogen is here. So according to the n plus 1 rule, that is 4 plus 1 equals to 5. This will give you the quintet. It clearly indicates that CH3 is here. Okay, so this will give you quintet. So I am writing quintet for this. And then the last one, this CH3, definitely 2 hydrogens are on the left hand side. So if you apply the n plus 1 rule for this one, in the neighbor you are having only 2 hydrogens. So 2 plus 1 equals to 3. So this will give you triplet. And if now you see the different kinds of the hydrogens which are present here, I already explained to you, in the mono-substituted benzene ring, this will produce a multiplet M, which is resonating at 7.1 ppm, near about 7.1 ppm. So you have fixed this sextate, which is this one, right? And then the quintet, which is this one, right? And then a doublet, which is this one, and then again a triplet, which is this one. Now you can go for the chemical shift as well. So you can see here, the most downfield signal will be due to the presence of the hydrogens on the benzene ring, which is resonated 7.1 ppm. So this signal, chemical shift somewhere around at 7.1 ppm. And you can see here, this hydrogen, which is only one hydrogen, is connected with the benzene ring, and the circulating electron cloud of the benzene ring will cause magnetic anisotropy, and due to the magnetic anisotropy, this sextate will be very downfield, and you can see it is resonating at somewhere around 2.6 ppm. So that sextate will be there at 2.6 ppm, right? And then you are having this quintet. So quintet for this one, only 2 hydrogens are here, and on the left hand side 3 hydrogens are there. So the magnetic anisotropy effect will be more on these 2 hydrogens rather than these 3 hydrogens. So second downfield signal, right, will be this quintet, and you can see this quintet is second downfield signal, resonating around somewhere at 1.6 ppm. So this quintet at 1.6 ppm. So I'm writing 1.6 ppm. Okay. And then you are having this doublet. And you know this doublet is due to the presence of this one, because magnetic anisotropy effect will be there for these 2 hydrogen in comparison to these 3 hydrogens, right? In comparison to these 3 hydrogens. So this will be next your third downfield signal, and that would resonate around somewhere at 1.2 ppm. So you can write the chemical shift for this one, 1.2 ppm, and your last signal somewhere around 0.8 ppm, which is this triplet. Okay, so this is the most probable structure given for this particular compound. You can take the screenshot because I'm going to solve the next problem. Okay, so I hope you have taken the screenshot. Now I am moving to the second part of the problem. So second one is also the isomer C10H14, and it is also the monosubstituted aromatic hydrocarbon. So one thing is clear, you are having the benzene ring. So now you can see here, again you are having the sextate, and for the sextate, if you want a sextate for this CH, there must be the presence of the 3 hydrogens on the right or the left hand side, and 2 of the hydrogens on the right or the left hand side. Anywhere you can put, I am putting on the right hand side. So like the previous problem, it will give you a sextate. There is no problem in that. Okay, and definitely this will give you what? Your doublet. So I'm writing D for this one. So you have confirmed this sextate. Okay, and there is no doublet. Please remember, there is no doublet. When doublet is not there, that means this cannot be your straightforward CH3. Well, you are getting a 2 triplets. So that means CH2 connected with the CH2, one triplet, and then again it is connected with the CH2, right? So if you check the splitting patterns. So for this, you will get n+1 rule. In the neighbor carbon, you are having 2 hydrogens. So for these 2 hydrogens, you will write 2 + 1, and this will give you a triplet. Okay. Particular for these 2 hydrogens, 2 hydrogens on the right hand side, 2 on the left hand side. If you apply the n+1 rule, 1, 2, 3, 4, 5, right? This is a quintet. However, the exact shape of quintet is not like that. It is according to the originally it is according to the Pascal's triangle. Okay, and for this one, if you connect with this one, again it will give you the triplet. Now you see, quintet you have proved, 2 triplets you have proved, what you left with the one of the sextate. So how this sextate is there? This is something very, very important which we need to clarify. So for this, what we can do, we can put CH3 here. So if I put CH3 over there, so this will also give you the triplet. If I do this, right, then definitely this information is wrong. Why? Because 3 hydrogens are here and 2 hydrogens are here. It can never be a triplet. So what we can do, we can delete this. So n+1, on the right hand side 3 hydrogens, on the left hand side 2 hydrogens. So it is nothing but 5 + 1 = 6. So this will give you sextate triplet. So 2 fragments are there, fragment number 1 and fragment number 2. And if you put these fragments together, getting a triplet. For this one, you will get a quintet, that is 5. Okay. And for this one, you will get a sextate. And for this one, you are getting a triplet. And what information we can get from the chemical shift values? You can see the most downfield signal is that 7.1 ppm. Obviously, this is due to the presence of these hydrogens which are connected to the benzene ring. The second one is the triplet one. Now you have to decide, you are having 2 triplets. One triplet is this one, another triplet is this one. Since you are having the 2 triplets, now it is your duty to decide this chemical shift, right, which this belongs to, whether to this triplet or to this triplet. Now it is quite clear, due to the magnetic anisotropy of the circulating electron cloud, these are very, very downfield, right? When they are very, very, very downfield, that means the triplet which is resonating at 2.8 ppm due to this CH2. Okay, so you can write this is 2.8, this particular signal, right? This particular one. And then you can see here, this quintet is quite fine, the second one. And then sextate again, very fine, to this one. And the triplet is very fine due to this one, because magnetic anisotropy, the effect of the magnetic anisotropy keeps on decreasing when we move throughout the chain from the right, from the left to the right. So magnetic anisotropy will be most due for this one, so that's why it is very, very downfield, and least for this one, that's why it is most upfield, which is this triplet. So this is how the proton NMR spectrum are useful in deciding the 2 different isomeric structures. Okay, and the problem I have taken from the Pavia Lampman spectroscopy book, chapter 3, problem number 24 in the exercise. Okay, so what is the problem? The following compounds are isomers with the formula C10H12O. Their infrared spectra show strong bands at 17-15 centimeter inverse and in the range from 1600 to 1450 centimeter inverse, right? Draw their structures. So this is the problem which you have been given, and here is the proton NMR data for the isomer A. You are getting a signal at 7 ppm, right? 7.1 ppm, and it's a multiplate. So it clearly shows that the presence, benzene is present here. So this signal may be due to the benzene ring. Okay, and then you are having the quadrate here, and then you are having the triplet here. Okay, and then this is the singlet one. So first of all, see, our usual routine is what? To calculate the hydrogen deficiency index, right? So for this particular formula, which is your C10 H12O, right? I am calculating HDI, hydrogen deficiency index I am writing, and the formula for hydrogen deficiency index is 2 times N plus 2 minus M times H divided by 2, where N is the number of the carbon atoms. Okay, so 2 multiplied by 10, because 10 carbons are there, we'll add 2 here, and total number of hydrogens are 12, and this whole divided by 2, And if you solve this by using the bird mass, then you will find it is basically your 22 minus 12 over 2, that will give you 10 over 2 equals to 5. So your hydrogen deficiency index is 5. That means this molecule may have 5 double bond, right? And it may have, say, 5 rings, but the possibility of 5 rings is not there, because only 10 carbons are there. Even possibility of 2 rings are also not very comfortable with this molecular formula. Why? Because only 10 carbons are there. So, and the signal at 7 ppm, it is also suggesting that one benzene ring is there. Okay. And if you write one benzene ring, say I'm writing a benzene ring, okay, and if you put 3 double bonds in the ring, so this completes the index of hydrogen deficiency of 4. 3 double bonds, 1 ring, 3 plus 1, 4. You left with 1 hydrogen deficiency index. So there may be the another group. But again, if you see very strong band at 715 centimeter inverse, and I already told you in my number of lectures, whenever you are having a strong band, so I'm writing, whenever you are having strong band at 17, around 1700 centimeter inverse, right? So here it is exactly 715. This is basically the carbonyl group. And you know, the carbonyl group may present in the acid, it may present in the aldehyde, it may present in the ketone. But this 1715, as I already told you, whenever you are having this carbonyl group, and which is actually resonating at this carbon, what you say, resonating at 1715 ppm, basically it is the carbonyl of the ketonic group, right? So there may be a possibility that ketone is here. So you are having much information about this. First is benzene ring, which is confirmed from the signal at 7 ppm, okay, and also the index of hydrogen deficiency 5. See, 1 double bond, 3 double bond, 4 and 5. So see, one thing is sure, with the help of your hydrogen deficiency index and your strong band at 1715 centimeter inverse, right, and your signal in proton NMR, the signal at 7 ppm, that your molecule is having benzene and this particular carbonyl group, okay. And then you are having the singlet over there. That means, and this singlet is way downfield, it is at somewhere around 3.8 ppm, okay. And then you are having the quartet and the triplet. And I already told you many times, quartet and triplet, you are, if you are having, it clearly indicates the presence of this ethyl functionality, right? And I already told you many times, so this will produce a triplet and this will produce a quartet. How? See, for this, if you apply the n plus 1 rule for splitting, number of splitted peaks, so you are calculating for these 3 hydrogens. In the neighbor, you are having the neighboring carbon, you are having 2 hydrogens only. So this will give you what? 2 plus 1, right? And 2 plus 1 equals to 3, which is nothing but your triplet, okay. So this particular signal, which is the triplet, right, this particular one, this triplet is basically due to the CH3. Later we will decide where we will connect, where we can connect the CH3, which carbon or which oxygen or which carbonyl, will decide this later, okay. And then if you see this quartet, so this quartet basically is the signal due to the CH2 group, which is this one, okay. And then you are having this signal, which is for benzene ring, benzene phenyl hydrogens, right? And then you left with this one only. So if you count the total number of carbon atoms, 6, 7, 8, but you are having 10 over there, okay. So we are 6, 7, 8, 9. So you left with 1 only. So where we can add that 1, where we can put this 1 carbon. So in order to decide the structure, first of all, what we can do, we can connect the pieces together, okay, because we are having this carbonyl and this carbonyl is connecting with this one. So if I draw the structure, so I can write my CH3 here, okay, and it is connected with the CH2. I can do just like that, okay. And then you see this quartet, basically, if I go back, this quartet, which is due to the CH2 group, it is at 2.5 ppm. And many times in my previous lectures, I already told you this signal, which is resonating at 2.3 ppm, is basically the de-shielded signal, generally by the presence of the carbonyl group. And carbonyl group is also confirmed from this data of 17-15 centimeter inverse, which is given in the question itself. So this CH2 is basically connected with the carbonyl group. That's why it is resonating at 2.0 ppm. Otherwise, if it was not connected with this carbonyl group, it would resonate somewhere around at here 1.2 ppm or 1.3 ppm, right? It will be very close to the CH3 group, but it is very far from the CH3 group, resonating at 2.2 ppm somewhere. It is indicating that the CH2 is connected with the carbonyl group. So what I can do next, I can connect this carbon with the carbonyl group, right? So now if you see, this will produce a triplet, very fine, no problem in that. And this will produce a quartet, no problem in that. And then you are having the singlet somewhere. See where you are having the singlet? This singlet you are having, which is resonating at 3.8 ppm, it is downfield signal. When it is downfield signal, so one thing is sure, these are the hydrogens which actually is which are connected with both the carbonyl group as well as the benzene ring, because carbonyl group alone cannot shift the signal way downfield at 3.5 ppm. For the signal to appear at this particular range 3.8 ppm, it required that there must be the two effect which is operating on this thing, on this particular signal. So one effect will be your magnetic anisotropy created by the circulating electron clouds in the benzene ring, and second, it is connected with the carbonyl group. So what I can do, I can immediately connect this CH2 here and benzene ring here, okay, which will create the magnetic anisotropy. And then you can see here, this will produce only one singlet. Why one singlet? Because see here, there are no hydrogens to split this the signal of these two hydrogens, and on the left hand side as well, there are no hydrogens present to split this signal. So that's why it's appear as a signal, as a singlet actually, right? And if you count the total number of the carbon atoms, then it is your what? C10, and then you are having 5, 5, 10 and H12 and then O. And don't forget, you are having 5 hydrogens connected with this, okay? So what I can do, I can mark these hydrogen as HA, type A of the protons. Why? Because the environment of these two hydrogens, on the top is the CH2 group, and on the bottom it is connected with this hydrogen and with this hydrogen. So the environment of this hydrogen and this hydrogen is same, so they are of the same type. But if you go through these two hydrogens, they are different from these HA, because their environment is what? On the bottom it is HA only, and H only, and on the top it is H of this and H of this, okay? So these two hydrogens are quite different from these two HA. So second set of hydrogen I can mark as HB and HB, and of course this is the third set, which is entirely different from these two hydrogens and these two hydrogens. So the signal of these two hydrogen will be splitted by these HB, and these HB signal will be splitted by this HC as well as this HA. So we'll get a multiplet, very complex splitting we will get for these 5 different kinds of the protons. So what I can do, I can write these hydrogens signal as a multiplet, right? Very complex splitting pattern you will find, and the signal will appear somewhere around at 7.2 ppm. If I go back, right, here I'm going back, so this signal at 7.2 ppm, it's a very complex signal, right? Splitting, very complex splitting is there due to the different natures of the hydrogens connected with it. So this signal is resonating at this particular value, right? And then you are having the signal of what this CH2, which is the singlet, and this singlet, if you see, it is appearing somewhere at 2.3 ppm, not 2.3 ppm, very far. Let me check where it is. Yes, signal at here, you see, 3.6 ppm, somewhere around at 3.6 ppm. Okay, so this signal is at 3.6 ppm. So I am writing this as 3.6 ppm. Why 3.6 ppm? Because two electron withdrawing group. This is the electron withdrawing group which will de-shield these hydrogens. Second, these protons, right? This circulating electron cloud which will de-shield these hydrogens. That's why it is appearing at 3.6 ppm. Otherwise, it would appear, right, if it was not connected with this phenyl, only with this carbonyl group, if it was connected, then this signal must appear somewhere at 2.0 ppm. But it is resonating at 3.6 ppm. It clearly indicates two different kinds of the factors are operating to de-shield the CH2 hydrogens, right? And the chemical shift of this CH2, which I already told you, it is a quadrate and resonating at 2.3 ppm, and this is your triplet resonating at 1.0 ppm. Okay, and then this bond, this stretching frequency in the IR spectrum at 1715 centimeter inverse. It's a polar group, so it will be a very, very strong band. And then if I go back, I'll find the another data between 1600 to 1450 centimeter inverse. Again, it's a very important indication. 1600 to 1450 centimeter inverse. This region basically belongs to carbon double bond carbon, right? And you are having number of bands here in this particular range. See, and the range and in the range of this 1600 to 1450 centimeter inverse, you are having the very strong bands. Okay, so these bands are due to the presence of the double bonds present in the benzene ring, right? So this basically is due to the benzene ring, these double bonds, right? So this signal is due to these double bonds. So I hope this is the correct structure. This is looking like the correct structure for this particular compound. So if you want to write the IUPAC name of this particular compound, so it is, see, this is your 1, this is 2, this is 3, and this is 4. So this is your 1 phenyl, right? And then butanone. So this is the IUPAC name of this particular compound. I hope this is quite clear to you. Now let's move further to check another isomer for this particular compound. So because this is the isomer, right? And if it is the isomer, one thing is sure, that means presence of the benzene ring, this is sure. And since it is the isomer, so this functionality is also it may also present in here. Okay, now you see, this is the singlet, very large singlet appearing at 2 ppm. So this is signal which is not splitted, but here you are getting the pair of the triplet. So many times in my lectures, I already told you, whenever you are having the pair of the triplet, that means you are having this CH2-CH2 linkage, right? This signal will be splitted by the neighboring two protons as triplet, as well as this will be splitted by the neighboring two protons. If you want to split the signal clearly, so you will apply the n+1 rule. That means you are calculating the splitting pattern of these two hydrogens. So in the neighbor you are having the two hydrogens, that means n is basically 2 for these two hydrogens. So what I can do, I can write 2 plus 1, and 2 plus 1, I am getting this 3, which is a triplet again. And same is true for this one. If you are calculating the signal for these two hydrogens, so in the neighbor you are having these two hydrogens, so again you will apply n+1 rule. So this will give you 2 plus 1, and again you are getting the triplet 3, and it's a pair. Please remember, it's a pair, not much difference in the chemical shift of these two signals. That means their environment more or less will be the same. And benzene ring is again there, very complex splitting pattern, as I have explained in my previous previous isomer, right? So this again is having the benzene ring, right? And these are the two triplets and the singlet. And then what we can conclude, actually, what structure we may have. See, one thing is sure, this unit I am having, this unit I am also having, and the third unit I am having, which is this one, right? So if I connect all these, right, and then you are having this singlet over there, and the intensity of this singlet is very, very high. So this may be, right, I'm not sure, but this may be due to the presence of this CH3. So if I connect all the pieces together, piece 1, and this is piece 2, this is piece 3 and piece 4, I may arrive to the structure of the compound. Okay, so I am putting my, say, benzene over there, and for benzene I am putting these 3 double bond in the ring. Okay, and then this is confirmed that I am having this unit, 2 triplets I am having, and since I am having the triplet only, so it must be the carbonyl group. Okay, why? Because this CH2 will only couple with these 2 hydrogens to give a triplet, which I have already explained to you. Similarly, these 2 hydrogens will only couple with these 2 hydrogens. There are no hydrogens present on this benzene ring, so it will produce a triplet again. So I am putting my triplet over there. There is no problem in that. And of course, these are the hydrogens like your previous isomer where I have explained the complex splitting and it will give a multiplet. Okay, and then you left with CH3 only. Okay, and this will produce a singlet only. Now one thing is sure, you see this CH3 is connected with the carbonyl group, and this carbonyl group will shift the signal of this methyl downfield between 1 to 2 ppm, right? And it is exactly resonating at 2.1 ppm. So what you can do, you can write say its chemical shift at 2.1 ppm, and this CH2 is connected with this carbonyl only on the left hand side, right hand side. On the left hand side it is connected with the CH2, so only the de-shielding which will be provided to this these 2 hydrogens by the carbonyl only. So this signal must be upfield signal. So in the pair this particular signal, right, which is appearing little upfield, not very much, but little upfield, this may be due to this CH2, and the chemical shift may be say 2.6 or the 2.7 ppm, just like that. Okay, and now you can check this CH2, because this magnetic anisotropy is there, and this magnetic anisotropy will put this signal way downfield, because 3 different kinds of the double bonds, 3 double bonds are there. So the downfield shift will be little higher for these hydrogens, and it will resonate around 2.9 ppm. Okay, and this is true that you are having signal at 1715 centimeter inverse in the IR spectrum, and various double bonds are also present between 1600 to 1450 centimeter inverse, as I have explained in my previous slide. Okay, so this could be the correct structure. Okay, so if this is the correct structure, then what is the name of this particular compound? So to name this, say this is your carbon number 1, this is carbon 2, this is carbon 3, this is carbon 4. So it is basically your 4-phenyl. It is your 4-phenyl, and then butanone 2. Butanone 2. So these are the 2 structures. The first one was this one, which is your 1-phenyl butanone 2, and the second structure is basically your 4-phenyl butanone 2. So this is how you can differentiate between the isomers by using their IR spectra and the proton NMR data. This is the problem number 25, which is given in the chapter 3 of Pavia Lampman spectroscopy book. Okay, so without wasting time, we will see how we can arrive the correct structures for the given molecular formula with the help of the proton NMR data, which is given in the question itself, right? So what is the question? The following 4 NMR spectra of isomeric mono-substituted aromatic ester. So first of all, you should know this thing is given to you. Aromatic mono-substituted esters. Right? This is given to you, and with the molecular formula of C10H12O2. Again, the molecular formula is also given. Make no attempt to interpret the aromatic proton areas between 7.1 to 7.4. Draw the structures of the compound. So these are the 4 spectra rather, okay, which you have been given in the question. Okay, and the molecular formula of the compound is C10H12O2, and you don't worry about this particular signal, which is resonating at 7.1 ppm here. Okay, and you have to decide what is the correct structure for the 4 different isomeric esters. So this is C10H12O2. One thing is sure, which is given in the question itself. First is the benzene ring. Okay, you know this is the benzene ring, and second is the ester linkage, C double bond O O. These things are given here. If you calculate the HDI, hydrogen deficiency index, for this particular given formula, then you will find the value will be 5, and which correspond to the one ring, your 4 double bond. So I am not going to calculate the hydrogen deficiency index in this particular example, because there is no need to calculate it, right? If you want to calculate, then you can go to my previous lectures where I have discussed how we can calculate the hydrogen deficiency index. But in this particular example, there is no need to calculate this because it is already given in the question. So only with the help of the proton NMR spectrum you can arrive the correct structure of the molecule. Though I have written the combined spectral problem here, but only the proton NMR data is given here, and we will decide on the basis of the proton NMR only, right? So you can see here, this is my quartet, okay, quartet, and this is my triplet. And there is a very big difference between the chemical shift of the triplet and the quartet. And this quartet is basically highly de-shielded because it is resonating at 4.1 ppm. But this quartet and triplet is a typical splitting pattern of the ethyl group. If you have this CH3 and then you are having this CH2, this forms a typical splitting pattern of quartet and the triplet. How? However, I have solved this particular type of the examples in the previous classes as well, but here again I can explain you how we can calculate the splitting pattern of this CH3, right? So splitting pattern means the number of the peaks in which your particular signal will split. So n plus 1 is the rule. And in the neighboring, if you want to calculate, right, if you want to calculate the splitting pattern of these 3 hydrogens, so you need to check the hydrogens which are just present at the adjacent carbon atom to this particular methyl group. Okay, so if you see, then your next carbon is having only 2 of the hydrogens plus 1, that will give you the 3. So that simply means this particular methyl group will split into a triplet. Similarly, if you want to calculate the splitting for this one, again you will follow the n plus 1 rule, and according to the n plus 1, where n is the number of neighboring hydrogens, which are 3 in this case, so you will put 3 here, okay, plus 1, that will give you 4. So this methylene will give you a quartet. So this is exactly is given here, quartet, and it is a triplet. But the very important definition is very important information which you are getting from this spectra is that this quartet is at 4.1 ppm. That means this CH2 is highly de-shielded, it is resonating here. So basically this particular signal is due to the 2 methyl protons. So since it is it is having very large chemical shift, that means this CH2 is connected with the oxygen. You know, electronegative atom causes splitting, right? Causes downfield shift. So how we can arrive the correct structure? See, this is given to you in the question itself. The benzene ring is present here. It is given in the question. And it is mono-substituted. Mono-substituted means only one substitution is there. Okay. And you know you are having this CH3 and then you are having this CH2. Since this CH2 is resonating at 4.1 ppm, it indicates that it is connected with the highly electronegative oxygen. This is sure, right? And then after that, what can happen? Since it is a ester linkage, so this should be carbon double bond oxygen. Okay. And then you are having another thing, which is the benzene ring, right? I am writing the benzene ring like that only. So if you count the total number of the carbons, 6, 7, 8, 9. But in your formula, it is given 10. So how we can arrange this next CH2 group? The only possible way is to connect this with the CH2, right? If you put these two pieces together, then you will find this is your benzene ring, and this benzene ring is connected with the CH2, right? And then this is your carbonyl group, and this is your oxygen connected with the CH2 and then connected with the CH3. If you count the total number of the carbon, it is now C10, and if you count your hydrogen, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens are there, 2 of the oxygens are there. So if you go back to the structure, right, if you go back to the spectrum, so again you can see here what is given here. I am drawing your structure again. This was your benzene ring, and this is CH2. There is no problem in that. Okay, let's move. Okay, fine. And then your carbon double bond oxygen, and this is your oxygen, and this is your CH2, this is CH3. So this structure I have concluded for this particular molecular formula. So now it is quite clear. So this CH2 will give you a quartate resonating at 4.1 ppm, and this CH3 will give you a triplet. So I am writing T for this one, and the chemical shift is this for 1.1 ppm. Okay, so this particular signal, which is a triplet, is due to this CH3. We don't need to worry about this particular signal, as it is already given in the question. Don't interpret the aromatic proton, right? And no other signal is present over there. However, it would be good if we have another singlet present in the spectrum, okay, which will prove the presence of this particular CH2 group, right? But whatever the data is given in the question, with the help of this data, it is sufficient to conclude that this structure is this particular one, and the name of this structure is this is your ethyl, okay, and then phenyl acetate. So this is the answer for the first one. Okay, now moving to the next one. The same thing is given here, C10H12O2, because this is the isomer, and here you can see you are having 3 different peaks. A very large singlet is given here, which is having the very high integration. Okay, and then the pair of the triplets, this is the pair of the triplet, that means 2 triplets are there. And how we can say that 2 triplets are there in the structure? CH2 connected with the CH2. If this system is there, then definitely this CH2 will give you a triplet, provided there are no other hydrogens on the left hand side, right? CH2 is having these 2 hydrogens over there, so 2 plus 1, that will give you 3. So it will produce a triplet. Same is true for this one. This will again give you the triplet, provided there are no other hydrogens are present on the carbon which is on the right hand side. So again, if you calculate the splitting pattern for this one, okay, so this will again come same. So this will also give you a triplet. Okay, how? Because only 2 hydrogens are here, n plus 1 rule, same thing. So this is sure that this CH2 system is present in your structure. Okay, and now if you focus on the two triplets, right, these 2 triplets, so they are very close. That means the environment of these 2 are somewhat same, not identical but same. But this one is basically your downfield signal. Chemical shift for this one is somewhere around 2.9 ppm. Okay, and for this one it is somewhere around at 2.6 ppm. Okay, so there is not much difference between the chemical shift of these 2. But this is this signal, which is downfield signal, it must be connected to some of the electronegative group, but not directly to the oxygen, because oxygen shift this particular signal way downfield, but it is present at 2.9 ppm. It clearly indicates that this particular is connected with the carbonyl group. Okay, so I'm telling you this particular signal, right, it is due to the CH2 group which is connected to the carbonyl group. So one thing is sure. So what we can do? We can write CH2, and then again we can write CH2, and then we can connect this with the carbonyl group. Okay, now you can see here, this is actually your 2.6 ppm, somewhere at 2.6 ppm. So how we can get the 2.6 ppm? So before going into the 2.6 ppm, what I can do, I can make this as ester. Okay, I'm making it ester. But another very important feature you are finding here, the signal at 3 point, somewhere at 3.8 ppm. So I am writing the chemical shift of this as well. So this is basically your singlet. Okay, so these were the triplet and triplet. This is your singlet, which is resonating at somewhere at 3.8 ppm. And you see the integration of this signal is very, very high, which clearly indicates the larger number of the protons, and it is a singlet only. And you know, only CH3 can produce this type of the signal. Only CH3 can produce this type of the signal. And this CH3 must be connected to the highly electronegative atom because it is resonating at 3.8 ppm. So what I can do, I can connect this oxygen with the CH3. Okay, so this could be the one of the fraction of this one. And then what you left with, the benzene ring. So you can connect this with benzene ring. Okay, and now if you want to decide the chemical shift, right? So what I can do here, I can write the chemical shift of this one. So this CH3, which is resonating at 3.8 ppm. So this signal, I can write this signal as what? It is a singlet having the chemical shift of somewhere around at 3.8 ppm, right? This is clear. Okay, and then this particular CH2 group, which will produce a triplet. Okay, because it is connected with the carbonyl group and it is more close to this electronegative oxygen. So this signal will be downfield compared to this particular CH2. So this CH2 is basically this particular one, which is at 2.9 ppm. Okay, so this triplet I am writing here at 2.9 ppm. I am writing here. Okay, and then you are having this particular signal. Again, it will produce a triplet, but this triplet will resonate at little upfield, which is where this 2.6 ppm. Okay, so I'm writing here 2.6 ppm. Okay, so this should be the correct structure for the second isomer based on this particular data. Why this signal is resonating at 2.6 ppm? Because due to this benzene rings circulation of the electron cloud, which produces the magnetic anisotropy, and due to this anisotropy, these hydrogens will go little, you see the downfield. Okay, and you should know one thing, that the circulating electron cloud will not shift the signal way downfield as it is shifted by the electronegative oxygen. That's why it is resonating at 2.6 ppm. It is resonating at 2.9 ppm, and it is giving a singlet here. So this is the correct structure for this one. We don't need to worry about the signal of this particular benzene ring because it is already given in the question. So what is the name of this particular compound? So this is how you can do. See, this is 1, this is 2, this is 3. So carbon number is 3, is having this phenyl, which I have written over there. This is the acetate part, and this oxygen is connected with the methyl. So this is the correct structure for this particular formula. Now moving to the next spectrum, what it says. Again the same, because we are dealing with the isomers, and now you are having these, see, you are having these two triplet, but these are not in the form of the pairs. There is a very large difference. One is resonating at 2.9 ppm. So I am writing this signal, right? This signal and this signal, and again you are having this particular signal. So these three signals are there. So it is resonating at, you see, nearly 4.1 ppm. Okay, it is a triplet again, and it is resonating at 2.9 ppm. Okay, and it is again a triplet, and this is a singlet which is present at 2.0 ppm. Okay, so what information we can get from here? So two triplet means, you know, as I already told you, CH2 connected with the CH2, they will produce a two triplet, as I have explained in my previous slide. But one triplet is way downfield at 4.1 ppm. It is quite clear that it is connected with the oxygen, right? It is connected with the oxygen, right? And then again you can see here, this particular singlet, right? So this is the singlet which is at 2.0 ppm. This singlet must be the singlet of the methyl group. Integration is very high for this one compared to these two. Okay, so this basically is representing the methyl group. So I'm writing CH3 here. But the important thing which you will note from this particular signal, it is resonating at 2.0 ppm. That means my methyl is connected with the carbonyl group. My methyl is connected with the carbonyl group. So what I can do, I can put C double bond over here like that and put CH3 here. I can write just like that. Okay. So if I write the chemical shift for this one, so this signal is basically due to the, I'm writing singlet for this one and 2.0 ppm. This is quite justified that it is resonating at 2.0 ppm because this carbonyl group, which shows the minus I effect, will shift this signal downfield from 1 ppm to 2.0 ppm. Okay, that's why this signal is here. And this CH2 is connected with this oxygen. It must be the downfield signal. And this is basically your triplet. Okay, and this triplet is basically this particular one at 4.1 ppm. It is resonating at 4.1 ppm. So I'm writing it 4.1 ppm. Okay. Now if you count 1, 2, 3, 4, 4 of your carbons are engaged here, and then you are having this benzene ring. Okay. And again, you see, due to the anisotropy produced by the circulating electron cloud, this signal will shift the downfield, will go to the downfield. But as I already told you, the double bond, this circulating electron cloud, will not shift the signal way downfield as it is done by the oxygen. So it will be slightly upfield signal, and this signal is at 2.9 ppm. So this is your triplet again, and that triplet is present at 2.9 ppm. Okay, so this is just looking like a correct structure for your formula. Okay, so we can conclude this as the correct structure. So how we can write the name of this particular compound? It is, this is 1, this is 2 phenyl, right? This is 2 phenyl, and then you have this ethyl part. Okay, 2 phenyl ethyl, and that fraction is basically your acetate fraction. So this is the name of this particular compound. Now moving to the last option, this is option D, again isomeric structure, and you see the quadrate at way downfield at 5.8 ppm. So I'm writing the chemical shift of this one. It is somewhere around at 5.8 ppm, and it is a quadrate. Okay, it is a quadrate, right? Earlier one we were having the triplets. Okay, but here now I am having the quadrate. Okay, so and then you see this particular one, this is your doublet, and it is resonating upfield, which is at 1.3 ppm. The scale is given here. Okay, and then you are having this one, which is a singlet at 2.0 ppm. So one thing is quite sure, your CH3 is connected with the carbonyl group. Okay, that's why only this is the only way by which this CH3 can produce a singlet which can resonate at 2.0 ppm. And then you can see here my quadrate. Quadrate means this particular proton, and you see the intensity is very low for this particular signal. That's mean the number of this particular hydrogen, that means the integration is very low. That means hydrogen, number of hydrogens are very low or is very low. Okay, there may be the presence of some methane kind of the hydrogen, that is only one hydrogen may present. And now what I can do, say if I put my CH here, and if I connect my CH with the oxygen, right, there is no problem in that. And again I'll give you the anisotropy due to this particular phenyl group. Okay, so this signal can actually go way downfield. Why? See, first of all, I am deciding why this signal is resonating at 5.8 ppm. Where it is written? Yes, 5.8 ppm. I am deciding this one. It is connected with the oxygen, which is giving the downfield shift. And again, remember, this is the only one hydrogen. So the effect of the electronegative oxygen will be very high on this particular hydrogen, and it will try to shift this signal of this hydrogen way downfield. And again you see, due to this anisotropy, right, produced by the benzene, circulation of the electrons by the benzene ring, this will also shift this signal way downfield. So here two factors are working. First factor is the anisotropy produced by the circulating electron cloud present on the benzene in the benzene ring, and due to this electronegative oxygen, that's why this signal is going way downfield at 5.8 ppm. But it is a quadrate. Quadrate means it must be linked with the three of the hydrogens in order to split it. Okay, in order to split it. So how I can split this signal? I can put CH3 over there. If I put CH3 over there, and if you apply the n+1 rule on this particular one for splitting, so number of neighboring hydrogens are 3. So you can put 3 over there, plus 1 equals to 4. So this will produce a quadrate. Okay. So that's why it is quadrate and downfield shift. Okay. So this thing is present here. And then what I can do here, and then I am having a doublet as well, right? Please remember, I am having a doublet here, doublet as well. This doublet is basically for this particular methyl group, right? If you calculate the splitting for this particular signal, so again you will apply the n+1 rule. Number of neighboring hydrogens are 1 or is 1 only. 1 plus 1 equals to 2. So this is the doublet actually. Okay, and this doublet is present somewhere at 1.3 ppm. This is quite clear, right? This fraction is quite clear. And then we know my compound is the ester. So what I can do, I can put carbon double bond oxygen over there. This is my ester linkage. Okay, and then what I can do, I can put my CH3 over there. And then you see in the spectrum at 2.0, right? At 2.0 you are getting a singlet, and for this singlet, this singlet is for this particular one. I'm writing singlet at 1.5 ppm, somewhere around at 1.5 ppm. Let me correct it. This is at 2.0 ppm. I'm sorry, I made a mistake. Okay, so this signal for this particular one. Okay, carbon number 1. So 1 phenyl, this is 1 phenyl, and then your ethyl acetate, 1 phenyl ethyl acetate. So this is how you can draw the structures for the isomeric compounds as well, with the help of the proton NMR only, right? Problem number 26, which I have taken from the Organic Spectroscopy book by Pavia, Lampman and Kriz, and this is the 26th problem of chapter 3, proton NMR spectrum, right? And what is the problem? Along with the following NMR spectrum, this compound with molecular formula C5H10O2 shows a band at 3450 centimeter inverse, and it is broad in nature, and 1713 centimeter inverse, a very strong band in the IR region. Draw its structure. Okay, so this is quite simple looking problem. You have been given this formula C5H10O2, right? So what you can do, you can calculate the index of hydrogen deficiency, or HDI. Okay, and the formula of HDI is 2n plus 2 minus m times h divided by 2. Okay, where your n is the number of carbon atoms and m is the number of hydrogen atoms. So if you calculate this, then you will find 2 times 5, because 5 carbons are there, plus 2 minus 10 divided by 2. So this will give you 12 minus 10 divided by 2 equals to 2 by 2, and you will get 1. So index of hydrogen deficiency is 1 in this case. Okay, so what it means, the HDI 1, what it indicates? Okay, it indicates your molecule is having one ring. This is first possibility. And second possibility, your molecule may have one double bond. Okay, but you can see here, in this case only 5 carbons are there. Okay, so there is no possibility of benzene for this particular molecular formula, so we can discard that benzene structure. And along with the benzene, we can also discard the other heterocyclic compounds and the small ring compounds, because the proton NMR spectrum is quite simple and it is not giving any special information. Similarly, IR data is also very specific in this case, and it is not representing any kind of the CH stretching and other things which indicates the other types of the compounds. So basically, first possibility you can immediately discard, and second possibility that your molecule is having basically one double bond. Okay, so this you can check. And one very important information you can see here, what we are observing a band which is broad in nature, and it is at 3450 centimeter inverse, and you know this is the region of the OH group, right? OH group, and it is broad, that means it is hydrogen bonded. Broad means hydrogen bonded. So I'll write BROAD, broad, and hydrogen bonded. So hydrogen bonding is also there, because intermolecular hydrogen bonding distort the shape of the band and make it broader in nature. Okay, so this proves. And then another very important aspect you can observe here, which is your 1713 centimeter inverse, a very strong band. Okay, at 1713 centimeter inverse, and this is clearly a region of the carbonyl group. Okay, and this carbonyl group is basically may present in your acid, it may present in the ketone, right? Because the range of the ketonic carbonyl group and acidic carbonyl group is very close. So whenever you are having these two possibilities like C double bond O and OH, so one may confuse, one may have this confusion that molecule is having this acidic group. Okay, but please remember, if acidic group is present in the molecule, then this hydrogen in the proton NMR spectrum, in the 1H NMR spectrum, will resonate between 10 to 12 ppm. Okay, that means if it is the hydrogen of your acidic functionality, then there must be a signal between 10 to 12 ppm, corresponding to the integration of 1. But this information is not here in the picture. That means you can safely discard this possibility of acid in this case. Okay, so what other things we can have in this structure? So first of all, you can see here, this is not acid, but this is your carbonyl compound, and this is your ketonic compound, right? And you can see here, this is one singlet which is present at somewhere around 1.3 ppm. It is a singlet, so I am writing S for this one. There is no splitting pattern involved in it. Similarly, at 2.1 ppm, another singlet you are having. Okay, so this is also a singlet. There is no splitting again. And then you have this singlet, which is a very smaller one, right? And its integration is looking quite small. That means it is corresponding to the one hydrogen, and it is way downfield at 3.9 ppm. It must be actually the proton signal of this OH group. Okay, and again this is a singlet. That means all singlets are present in the molecule, and no other splitting patterns are given. So what we can do, we can try to figure out what actually we are having in this case. So what I can do, I can put this carbonyl group here. Okay, this is your carbonyl group. And then what you can do, and you know, ketone is always what? Ketone can never be terminal. Ketone can never be terminal. Okay, so it will present in the center. So what I can do, I can put this ketone here, and I can connect these four you see carbons here. Okay, and then what I can do, say this is where 1, this is 2, this is 3, and this is 4. So what I'll do, I can put 1 of OH here. Okay, so this will give you one signal, and this is CH3. This will produce another signal, and this is another CH3. This will produce another signal. Now if you check here, this CH3 will produce a singlet. Okay, because in the vicinity there are no other hydrogens present on this particular carbon to split the signal of this methyl group. That's why it is a singlet. And same is true for this one, another singlet for this particular methyl group's hydrogen. So I'm writing S here. Again, you can see there are no hydrogens attached here. No hydrogens are attached here. So one singlet is here, right? And then this singlet again due to of this hydrogen, and because this signal is connected with the OH group, so it should be very downfield. So now if you count total number of the carbon, so it is 4 carbons, but we are having the 5 carbons. And so what I can do, I can put one of CH3 here. So if I put one CH3 here, so this is CH3, this is CH3, these two are equivalent, right? These two equivalent, that means they form the same kinds of the set. Say I am calling this methyl as the set A of the proton. So this is also a set A of the proton. Why? Because the environment of this methyl group is this carbon, which is having OH group, and same is true for this methyl group, because this methyl group is also having the same environment of carbon, which carries this OH group. So these two are same. When these two are same, they will produce one singlet, right? And of course, the integration would be 6. Would be 6 for this one, right? So what I can do, I can go back. So you see this singlet, this one, this is due to the presence of the OH group. Okay, this one, and this singlet, you see this particular singlet. If I check here, you see this particular CH3 is connected with the carbonyl group, and this carbonyl group is electron withdrawing. This will de-shield this protons of this methyl group, and this shielding will causes the downfield shift somewhere around 2 to 2.5 ppm. So if I go back again, so this signal has 2.1 ppm, and this signal is basically due to the CH3, right, connected with the carbonyl. So this signal is due to this one, and of course this particular signal, which is having the very high integration of somewhere around 6, it is due to the 2CH3 connected with this. Okay, and OH is here. So this signal is present due to this one. So this particular structure is looking like the more probable structure uh, for the data which is given in the question. So on the only confusion which one can have is of having the acid functionality, but you cannot mark acid. You cannot see predict acid, because acidic proton will resonate between 10 to 12 ppm, which is not there. But one may also think like that your molecule may have some aldehyde. Okay, again it is not possible, because this aldehydic proton resonates between 9 to 10 ppm, and this signal is also not present in the proton NMR spectrum. So this is the correct structure of the compound, right? And if you know the say your carbonyl stretching frequency in the proton NMR spectrum, so this will somewhere around 1713 centimeter inverse, and this OH very broad and strong one, this will be present, or this is present actually in this particular range. Okay, and proton NMR spectrum I have already explained. Okay, so this is how you can go for the problems which are based on the different spectroscopic technique. 27, and the problem is very important for all the students who want to learn the details of the spectroscopy, or how to solve the problems based on the combined spectral problems will be the target, right? So this is the example, and what is the question? The following ester with the formula C5S6O2 shows medium bands in the IR spectrum at 3270 and 2118 centimeter inverse. Draw the structure of the compound, right? So it is already given in the question that the compound is the ester, so there is no need to worry about the other things. And in the IR spectrum you have been given two bands, and which these bands are medium intensity bands. That means the group which is showing these particular bands, they are not very much polar. In the proton NMR spectrum, you can see a quadrate is given here, which is way downfield at 4.1 ppm somewhere, and a one singlet which is at 2.9 ppm, and then you are having this particular triplet which is at 1.2 ppm. This is looking like exactly the problem number 28 which I have solved yesterday for you, right? So NMR pattern is the same. So how to solve the this particular problem? So I am going in my own traditional way. First we'll calculate the index of hydrogen deficiency, which will give you the information about the unsaturation present in the molecule or the number of the rings present in the molecule. So how to calculate the uh, hydrogen deficiency index? The formula is given here. HDI equals to 2 into N, where N is the number of carbon atoms and your carbon atoms are 5, which are given in the question, plus 2, and H is the number of the hydrogen atoms and number of hydrogens are 6, and this is divided by 2. Okay, and if you solve this, then you will find 10 plus 2 minus 6 over 2. This will give you 12 minus 6 over 2 and 6 by 2 and 3, right? So degree of unsaturation or hydrogen deficiency index is 3. So what is the meaning of index of hydrogen deficiency of 3? So if you are having 3, that means your molecules may have 3 double bonds, right? Your molecules may have 3 double bonds. It may have 3 rings, okay? It may have 2 rings plus 1 double bond, okay? It may have 1 ring plus 2 double bonds. It may have 1 double bond plus 1 triple bond. I am writing TB for the triple bond, right? These are the few of the possibilities, okay? But you can see here the molecular formula given is C5H6O2, C5H6O2. Okay, so only 5 carbons are there, which then that means there is no possibility of forming the ring compounds, right? You cannot guess that the molecule may have your benzene, because benzene is having 6 carbons and it is having the degree of unsaturation of 4. It is not possible. And lower membered compound, lower cyclic compound like cyclopropane, cyclobutane and other heterocyclic compounds are not also possible, because NMR is very simple and it is already given in the question that this is the ester. Okay, so what you can do, based on the information given in the question, you can quickly discard possibility second, possibility third, possibility fourth. So what you left with the 3 double bond possibilities and 1 double bond possibilities. But the important thing is that you can clearly observe a band, medium band. So I'm writing here medium, which you can observe at 3270 centimeter inverse. And see, this will prove that how important these spectroscopic techniques are, right? With the help of the spectrum, you can quickly go to the answer, right? You can quickly predict the answer. And if you know this is the medium intensity band, that means the bond is not that much polar, and this is somewhere around 3270, which is the region of your, say, you can say the hydroxyl group sometimes, right, or the NH group sometimes, but they are the very much polar and they give the very strong band, but it is 3270. And you know, when you have carbon triple bond carbon, and when this carbon triple bond carbon is having CH, so its CH stretch will resonate somewhere around at 3300 centimeter inverse. So it is looking like that your molecule is having this CH bond which is connected to the triple bond. But for this we need to confirm whether the triple bond is present in the compound or not. So you can go for second data of the IR spectroscopy, and you are having again a medium band. So I'm writing MB for this one. You will write the medium band, okay? And this you are observing at 2118 centimeter inverse, and this is the region basically which belongs to the carbon triple bond carbon. You cannot go for the carbon triple bond nitrogen, okay, which is slightly stronger. This bond is slightly stronger than the carbon triple bond carbon. It resonates somewhere around 2300, right? But this is quite clear that their molecule is having triple bond, because this 2118 centimeter inverse, this is the region of your carbon triple bond carbon. This is very important, right? Because the range of this carbon triple bond carbon is 2100 to 2260 centimeter inverse. So if you want to know the range, so in the next page I am writing the range here. Again, it is very important to learn the few ranges, right? range of carbon triple bond carbon stretching frequency, okay, and it is your 2100 to 2260 centimeter inverse, right? Similarly, you are having carbon triple bond hydrogen, C this carbon triple bond carbon connected to this hydrogen, and this is having a beautiful range from 30 to 70, 3270 centimeter inverse to 3330 centimeter inverse. And in the question you can see here, you have been given this value 3270 centimeter inverse, and this value in your question it is given at 2118 centimeter inverse. So if you put the pieces together, then you will find your molecule is already a ester which is given in the question. So for ester functionality, what you can do, you can go for, and second thing which is given in the question is the carbon triple bond carbon having the hydrogen, and this is exactly going with the hydrogen deficiency index which we have calculated. This is one double bond, this is the this correspond to the one HDI, and this is a triple bond. Remember, triple bond correspond to the 2 degrees of unsaturation. So 2 plus 1 HDI is actually the 3 in that case. Now what you can do, you can connect them, but before connecting these things you should know, if I go back, you see here one quadruplet is given and one triplet is given. And in the last lecture, I also told you it is a typical pattern of ethyl group splitting. Ethyl group splitting. How? Let us check. Say this is your CH3, right? Connected with the CH2, and this will produce a triplet. How triplet? You know, if you want to calculate the splitting pattern of this methyl group, so the formula is N plus 1, where N is the number of neighboring hydrogens, which are 2 in this case. So we'll put 2 here, 2 plus 1, that will give you 3. Okay, there is no problem in that. Similarly, if you want to calculate the methylene hydrogen splitting pattern, again you will use the rule N plus 1, right? And number of the neighboring hydrogens in this case is 3, right? And this will give you 3 plus 1 equals to 4, and so this is a quadruplet, right? And this is a triplet, and this will produce a singlet here. Okay, and you know this singlet resonate in the NMR spectroscopy somewhere at you can say 2.0 to 3.0 ppm. This is the range of the chemical shift in the proton NMR spectrum, right? And this triplet, if I go back again, you can see this quadruplet is way downfield. This quadruplet is way downfield. That means it is connected with the highly electronegative atom of the oxygen, but not to the carbonyl group. Suppose it is connected with the carbonyl group, then it must be resonate somewhere at 3.5 ppm, right? But it is way downfield, so it is quite clear that is quadruplet, which is due to the presence of the CH2 group. That CH2 group is connected with the oxygen. Okay, and this is the pattern. So what we can do, we can put the pieces together. I can write CH3 and then my CH2, because it is way downfield, somewhere around at 4.1 ppm. So it indicates that it is connected with the oxygen, right? And then your ester functionality, just like this, and then it is connected with the carbon, triple bond carbon and CH, right? So if you count the total number of atoms, carbons, 1, 2, 3, 4, 5. 5 carbons are there, C5 hydrogens, 3 to 5 and 1, 6. 6 hydrogens are there, and 2 of the oxygen atoms are there. So it is this structure is corresponding to this particular molecular formula as well. So this is looking like a correct structure. So this is the answer basically: CH3, CH2 connected with the oxygen and then the carbonyl and then the C triple bond CH. So if I write your answer again, this value is given at 3270 centimeter inverse. In the proton NMR spectrum, it is producing a singlet, and this singlet is present at 2.9 ppm value. Okay, this carbon triple bond carbon is also present in your compound, right? And the value for this, it in the proton NMR spectrum is given at 2118 centimeter inverse. Okay, and then this this triplet is given, and then this quadrate is given. Quadrate, it is resonating somewhere at 4.1 ppm. Okay, and this is a typical methyl, right, which is a triplet here. It is resonating at 1.1 ppm. Okay, so this much of information is given in the proton and the IR spectrum. This is the correct answer. So this problem is quite easy problem. The following compound with the molecular formula C7H12O4 shows strong absorption at 1734 centimeter inverse and has several strong bands centering at about 1200 centimeter inverse in the IR spectrum. Draw the structure. Okay, and in the NMR spectroscopy, in the NMR spectrum, only 3 peaks are given here. One is the quadrate, which is way downfield at 4.1 ppm, and a singlet, which is somewhere around 3.2 ppm, and a triplet, which is centered at at 1.1 ppm, approximately 1.1 ppm. So the methodology which I will use to solve this particular problem is the common methodology of my own, where first I'll calculate the index of the hydrogen deficiency, right? It is very, very important. So I'm calculating my HDI, hydrogen deficiency index. This will give you the probability of the presence of the number of double bonds and the rings at the combination of the two, right? And the formula for HDI is 2 times N plus 2 minus M times H divided by 2. Okay, so how we can solve it, where N is the number of the carbon atoms, and the formula, what is the formula given here? I'm writing this formula again here. C7H12O4. This formula you have been given, right? So only 7 carbons are here, so I'm writing 7 for this carbon, and then the plus 2 minus M is the number of the hydrogen, so I'm writing 12 over there and divided by 2, right? If you apply the Bode mass rule and solve this particular, 7 to the 14, right, plus 2 and then minus 12 over 2. Okay, this will give you 16 minus 12 over 2. That will give you 4 by 2 equals to 2. So HDI is 2. Index of hydrogen deficiency is 2, which I have calculated here. So what is the meaning of the HDI 2? Right? So you can see here. See, when you have the HDI of 2, right? So you have these 3 possibilities. First is 2 double bonds may be probable in your compound. 2 double bonds may present. Okay, and then second possibility is what? 2 rings may be present. Number 3, combination of this, 1 ring plus 1 double bond may present in your compound. Okay, and the formula is C7H12O4. Okay, and now see, you may think in this way, that 7 carbons are here, so there may be a possibility of having benzene ring for this particular formula, right? So but can we check? But we can check whether the benzene is probable or not. For this, we need to draw the structure of the benzene. Okay, in this benzene ring, 3 dBs are there, double bonds, plus 1 ring is there, and if you add the 2, so your HDI would be 4. Okay, but in the question itself, HDI is 2 only. So probability of benzene we can straightforward discard. Okay, and not only the probability of the benzene ring, any ring in this particular problem we can discard, right? So however, you may argue that there may be the presence of the 5-membered ring or the 4-membered ring and fused ring type of things. But in the proton NMR spectrum, if you see the proton NMR spectrum, the spectrum is quite simple here. Okay, there is no information regarding the presence of your heterocyclic compound. So if your heterocyclic compound is not present here, that means you can quickly discard these two probabilities, second and third. Only two double bonds are present in that in this particular problem. Okay, now the very important thing, if you go back, very important thing, you are having a very strong, shows a strong peak, right, at 1734 centimeter inverse. Strong bol raha hai, very strong, right? So you can write strong band at what? 1734 centimeter inverse. And you know your carbonyl group base value in the IR spectrum, base value for the presence of carbonyl group is 1700 centimeter inverse. So it is looking like that this molecular formula generally having this carbonyl functionality, but carbonyl group is present everywhere. It is present in the aldehyde, it is present in the ketone, acid, amide, and several other acid derivatives. But can we have the some more clear idea what kind of the carbonyl group is this? So for this you can recall this thing in the IR spectrum. Please remember, in the IR spectrum, ester carbonyl group, carbonyl functionality of ester carbonyl group resonates. So I'm writing resonates as well here, in the range of 1735 to 1750 centimeter inverse, and this is exactly given in the question. So that means this is ester carbonyl group, right? This is basically your ester carbonyl group. Ester carbonyl group is present. When ester carbonyl group is present, so what you can do, you can draw the functional group of the ester. So I am removing this thing here. So this is carbon double bond oxygen and this is O. And again you can go back and check, has several strong bands centering at about 1200 centimeter inverse. What it is indicating, right? You know, this carbon single bond oxygen, the range of the carbon single bond oxygen, the base value is in the range of 1000 to 1300 centimeter inverse, and you have been given the value at 1200 centimeter inverse. That means this functionality is present over there. So this you can confirm. This compound is the ester compound. If you count the total number of the oxygens, 2 oxygens are there, but in the formula you are having the 4 hydrogens. So there may be a chance that diester type of thing may be present for this particular formula. But before concluding that thing, I want to go to the proton NMR spectrum, right? Here you can see the proton NMR spectrum. So I'm removing this. No, I'm not removing. You can see the triplet, singlet, and the quadruplet. So now suppose in the question you have been given triplet in the question itself, right? And you have been given this quadruplet along with the singlet. Only these three things are there. How you get the, if you focus on this quadruplet and triplet, this is basically the typical splitting of the ethyl group. This is the typical splitting of the ethyl group. How? You can see, if you want to know the splitting pattern of this CH3 group, so for this you will apply this n+1 rule, where n is the number of the neighboring hydrogens, which are 2 in this case, 2 plus 1, that is 3. That means this CH3 is giving triplet. Okay, if you calculate this one, this will give you n+1, where n is the number of neighboring hydrogens, which are 3. 3 plus 1 equals to 4 quadruplet. So this is your quadruplet, which belongs to this one. So if you connect the two fragments, this is CH3, this is double bond O, and this is O. Okay, this is CH3, this is CH2, this is C double bond O, and this is O. Right? This could be possible, right? And another thing which you can think of, CH3, CH2O, C double bond O. These two you can think, okay? And now if you count the proton NMR signal, so triplet for this one, quartet for this one, same is true for these two as well, okay? And you are having a singlet again. Now how many hydrogens you left? See, this 3 to 5. If I go back, the formula was not go back, the formula was C7H12O4, just like that. So what I can do, say I am putting my CH2 here, just like that, okay? And then again this oxygen which is connected here, and then carbon double bond oxygen, and then CH2 and CH3. Suppose I have drawn in this manner, okay? The same I can do for this one as well. I can write CH2 here and connect this CH2 with the carbonyl group, and then oxygen here, CH2 and the CH3, right? These two possibilities I can make. Now, if you check this is quite clear. This particular CH2 group, which is in between the oxygen atom, right? It will show the singlet. Why singlet? Because there are no hydrogens to the neighboring atom. Okay, so there will be no splitting. So this singlet for this CH2. Quite clear? And same is true for this one. So this, if you draw the splitting pattern, triplet, quartet, singlet. Now the very important thing you can see here, this molecule is quite symmetric molecule. Quite symmetric molecule means you can put a plane of symmetry bisecting this methylene group into two identical half. So how? Say this is the plane of symmetry, and I can write it as sigma plane. So when you put the sigma plane here, you can see this left half, CH3, CH2, C double bond O, is exactly identical to the right half. That means this methyl group, which is A, is identical to this one. And you know, in the NMR spectrum, proton NMR spectrum, identical groups or identical protons will give the one peak only. So you will get only one triplet, but not two triplet, because due to the plane of symmetry, these two are identical, right? And same is true for this one. Say this is your B, and this B is exactly identical to this one, and you will get one quartet, not two quartet, because this CH2 is identical to this one. So two peaks you are getting here, and one singlet is here. This is quite fine, there is no problem in that. But same is true here as well. If you draw for this one, this will give you what? Triplet, and this will give you quartet, and this will give you singlet. Again, this is suppose set A, this is suppose set B. So this is again set A and set B. These two possibilities are there. See, what if I can think about other possibility as well? So before going for the other possibility, you can observe that another plane of symmetry is also there. That's why this half and this half identical. So next possibility could be like this: CH3, CH2, C double bond O, O, CH2, C double bond O, O, CH2, CH3. All are having the same molecular formula corresponding to the C7H12O4. You can count all the atoms if you want. Okay. But here you can see this CH2 group is connected to the carbonyl group, and this CH2 group is connected to the oxygen group. That means these two are not equivalent, and so does these two CH3. So you can quickly discard the third possibility. Okay, so this is not possible. Okay, now what other confirmations we can have regarding the first structure and the second structure, which one is the correct one, right? So for this you need to check the chemical shift. chemical shift values. Okay, chemical shift values given for this quadrate, right? For this quadrate, for example, this is given in the question, and let me check what is the value. The value for the quadrate is 4.1 ppm, right? So I'm writing here 4.1 ppm. Clear? And then you can see here in this case again this chemical shift. I'll come later on this. And then you are this CH3, which is somewhere at 1.2 ppm. It is given like that, 1.2 ppm. And this CH2, the value of this singlet, let me check. The value, chemical shift value for this singlet is 3.2 ppm, right? Quite good. 3.2 ppm I can write for this one, 3.2 ppm. Now we can see this CH2 is connected with the oxygen here, and similarly this CH2 is also connected with the oxygen here, right? Quite clear it is, this one, right? This CH2 is connected with the oxygen and oxygen here, and this CH2 is connected with this one and this one. This CH2 is connected with the carbonyl, and this CH2 is connected with the oxygen. And you see this particular one, this is typical acetal linkage. This is typical acetal linkage, this and this. And you know this oxygen is highly electronegative, so it will give you the way downfield chemical shift. And this quadrate is appearing way downfield, most downfield at 4.1 ppm. But if this CH2, when this CH2, if you consider this one connected to this one, this carbonyl group is also electron withdrawing, but it is not that electron withdrawing to shift this quadrate to way downfield at 4.1 ppm. So if you consider this one, then you are this CH2, right? This CH2 will be somewhere around, I'm writing 3.5 ppm. Typical methylene, which is connected with this carbonyl group, has the chemical shift in this range, 3.5, somewhere centered at 3.5 ppm. But when it is connected to the oxygen, it definitely gives this value 4.1 ppm. So this clears your doubt that first structure cannot be the correct answer based on the chemical shift. So it is very important to know the values or the range of the chemical shift as well. It is very good to have the idea about the splitting pattern all these things, but you have seen already both these compounds have correct splitting pattern, all these things, but you can see the correct structure is looking like the correct structure is actually the second one, because this is more consistent with the chemical shift. However, the splitting pattern is same in that case and in this case, right? So this actually molecule is looking the correct answer. So I am drawing this again for this one somewhere around at 4.1 ppm, I think. Let me go back. Yes, 4.1 ppm, and for this it is 1.2 or 3 ppm, whatever. And this singlet is appearing at, let me check, 3.2 ppm. 3.2 ppm. And this is basically your diethyl malonate. Diethyl malonate. Okay, so this is the correct answer. But if you think like this, okay, so this cannot be your correct answer. Why? Now this CH2 group is connected with the center wall. This one is connected with, is linked with the two highly electronegative oxygen, and this will shift the chemical shift way downfield if it is connected these two oxygen atoms, and it may go very downfield somewhere around say 4.5 to 6.0 ppm, right? So you can confirm that this is your correct answer. So this is how you can solve the problem based on the combined spectral problem. In today's class, I am going to solve another problem based on the combined spectral problems. And this problem I have again taken from the organic spectroscopy book by Pavia, Lampman and Kriz. And this is the problem number 30. And this problem is particularly important for the students who want to learn the NMR spectroscopy in the depth. Okay, because in this particular problem, we will use the depth NMR spectrum as well, along with the proton NMR spectrum and the carbon spectrum. Okay, carbon spectrum is not there, but certain values are there. Okay, so this problem is going to be very, very important. This compound has the molecular formula of C6H12O, which I have written over there. Interpret the pattern centering on 1.3 and 1.5 ppm in the proton NMR spectrum. You have been asked only one thing, that you need to, or you have to interpret this particular NMR pattern, which is in between the 1.3 and the 1.58 parts per million. That means this particular thing you need to explain why this typical splitting pattern is here. Okay, that's why this problem is going to be very, very special for you. Okay, so what we'll do, first of all, we'll calculate the index of hydrogen deficiency, or the hydrogen deficiency index. HDI formula is the 2C plus 2 plus N minus H minus X over 2. So here 6 carbons are there. So 2 into 6, that will make 12, and plus 2, that is 14. No nitrogen is present, 0. 12 hydrogens are present, minus 12. No halogens are there, 0 over 2, that is 14 minus 12 by 2, that is 2 by 2 equals to 1. So index of hydrogen deficiency in this particular formula we have calculated as 1, and this 1 indicates that your molecule may have the one ring, or it may have a double bonds. But in the IR spectrum, you can see here a band resonating at 1715 centimeter inverse, and it's a very sharp band and very strong band. Okay, and this 1715 centimeter inverse is a typical value for the aliphatic ketone. That means carbonyl carbon is present here. Okay, this carbonyl group belongs to the aliphatic ketone. This is the typical value. So you have identified this C double bond O. Okay, and then if you quickly see your proton NMR spectrum, so you are having this particular singlet over there, and this singlet is resonating at somewhere around at 2.0 ppm. It clearly indicates that its integration is quite high. That means these are the 3 protons, and it is these 3 protons are giving only one singlet. It clearly indicates that it is connected with the carbonyl group, as its chemical shift is also. So this fragment you have confirmed, CH3 C double bond O. This you have confirmed. Okay. Apart from this particular fragment CH3 C double bond O, nothing much is there in the spectrum to get idea about the other units present in the, or other groups present in the molecule. Whenever you have been given in your data this depth NMR, always try to interpret this depth NMR first. You must have an idea about the interpretation of the depth NMR spectrum. So this is the data for the depth NMR, and I hope you understand what is the meaning of the depth. DEPT, distortionless enhancement of polarization transfer. Okay, this is a special technique in the NMR. This will give you the idea about the types of the carbons present in the molecule, whether your carbon is connected with the one hydrogen, it is connected with the two hydrogen, or it is connected with the three hydrogens. Okay, so first of all, you see here depth 135 is given here, and these are the chemical shift values for the typical carbon, and this 200 is 13. It is the value of carbonyl carbon. Your remaining carbons are also there. 6 carbons are there, so 6 chemical shift are also there. One at depth 135. So what information we can get from the depth 135? See, your molecule may have this particular kind of the carbon. Your molecule may have this particular kind of the carbon, which is connected with the two hydrogen, and then the three hydrogens. These kinds of three hydrogens are possible whenever you are talking about the depth NMR spectrum. So this particular CH, right, this will give you the peak on the positive side. That means usual NMR peak, and the carbon which is having the three hydrogens over there, it will also give you the positive peak. That means your normal upright peak. Whenever your CH2 is present in the molecule, you will have the negative peak. Negative peak means peak on the bottom side. So for example, these peaks may belong to either CH3 or CH. But this negative peak always belongs to CH2, right? So this information we can get from the depth 135 NMR. So you can see here positive peak, positive peak, positive peak, positive peak. 4 positive peaks are there. In the depth, you can see here in the D, E, PT 135, 4 positive peaks. 4 positive peaks. 4 positive peaks means these 4 may be your CH, 3CH or 1CH3 or 3CH3 or 1CH or 2CH or 2CH3. Any combination could be possible, right? So these things are there. And then you are having, you can see here, this is your negative peak. Negative peak means your carbon which is connected with the 2 hydrogen, negative peak. Okay, so one negative peak is there. So I'm writing, it clearly indicates that your molecule is also having CH2 group. Okay, now then you can see your next one, your depth 90. So what information we can get from the depth 90 NMR spectrum? It is very, very important. Remember, whenever this depth 90, whenever the peak is present on the depth 90, it clearly indicates the methane hydrogen. That means CH is also present in your molecule. And this is no peak, no peak, no peak, no peak, no peak. That means only one carbon is like that, which is having the one hydrogen attached. You have confirmed only one CH. So what you left with, that means your molecule is having one CH here and 3 CH3. So now you have confirmed many things. So what things you have confirmed so far? I am writing here. You have confirmed the presence of carbon double bond oxygen connected with the CH3. This you have confirmed earlier. Presence of another 2 CH3 groups. This you have also confirmed. And then you have confirmed one of the CH2 group from the depth NMR spectrum. This is the negative peak. This negative is due to the CH2, right? And then from the depth 90, you have confirmed this CH. So you are having these things. These things you are having. Okay. Now what you can do, you can put them together to get the correct structure of the molecule. I hope you understood these much of things quite clearly. Okay. Now what we can do, we can put these pieces together to get the correct structure of the molecule. This is something very, very important. And one more important thing you can observe here, in this particular spectrum, where in the bottom part your depth NMR data is given, right? In the upper part, you have been given a triplet here, okay, and a doublet. Triplet and doublet you are having. So triplet, how you can get your triplet? Triplet you can get in this manner only. Your CH3 when connected with the CH2, okay, that means it will give you what? A triplet. So whenever you are calculating the splitting pattern of any methyl group, right? So say, for example, you are calculating the splitting pattern or splitting of the peaks for these particular 3 hydrogens. So you need to look on the hydrogens present on the neighboring carbon. So if you want to calculate the splitting pattern of these 3 hydrogens, you need to check the number of the hydrogens on the neighboring carbon. So neighboring carbon is this one and it is having 2 hydrogens only. So what you can do, you can apply the n plus 1 rule, where n is the 2 which are the neighboring hydrogens plus 1, that will give you 3. So this is how you can get the triplet. So now you have confirmed this thing, and now you have confirmed the connection in between these two. That means you are having CH3 and CH2 as well. Okay, and then you are having one CH this one and CH3 this one. Okay, so how we can connect these things? You can take the screenshot of this one. You are having this CH3, there is no problem in that, and then you are having CH2, again no problem, and then you are having this CH, okay, Along with the CH, you are having this carbon double bond oxygen and then CH3. These things are here. Okay. What you left with? You left with this methyl group. You left with this methyl group. So you can connect this methyl group over there. Say this is carbon 1, carbon 2, carbon 3, carbon 4 and carbon 5. So it is where 3 methyl pentane 2 one. So this structure could be the answer, okay? But we'll verify how we are having this particular answer, okay? So first of all, we need to check the splitting pattern. See, this will give you the singlet. S I am writing here, okay? And say this one, this will give you what? A triplet. And then you are having this. See this, why this is producing a singlet? Because there are no hydrogens present on the neighboring carbon. And why it is giving a triplet? As I explained here, because in the neighbor you are having the 2 hydrogens. And if you want to calculate the splitting pattern of these 3 methyl groups, so you need to look on the number of the hydrogens present on the neighboring carbon. So your neighboring carbon is having 1 hydrogen only. You will apply n plus 1 rule. So you can write n plus 1. That will give you what? 1 plus 1 equals to 2. 2 means doublet. So this will produce a doublet. This will produce a doublet. And you see, this doublet you are having here. This doublet you are having here. So many things you have confirmed. You left with the interpretation of this CH2 group, and then you left with the interpretation of this CH group. Rest you all have decided already, right? This singlet, this doublet, and this triplet. Now, if I go back further, say, this is the typical splitting pattern which you need to decide, and this is the typical splitting pattern which you need to decide. Okay. So what I can do, I can draw the previous structure very quickly. First of all, we'll decide the chemical shift, okay, for the hydrogens present in the molecule. So I'm telling you, this would be the most downfield signal. It is most downfield signal. Most downfield signal. Why? Because this hydrogen is connected with the carbonyl group, and carbonyl group is the electron withdrawing group. So it will de-shield these hydrogens, and de-shielding always causing the downfield shift. So in the entire molecule, this signal would be the most downfield signal. So straightforward, you can jump up to the conclusion that this particular splitting pattern is due to the presence of the CH. Okay. Later we will decide how we are having this particular set of the splitting pattern. And then you are having, say, next one is this one. This is your second most, not this one, very sorry. Now you can see this particular one, this is the second most downfield. Second most downfield signal. Why second most downfield signal? Because this is the alpha carbon and these hydrogens are alpha hydrogens. Similarly, this hydrogen is also the alpha hydrogens. So this carbonyl group will de-shield the hydrogens of this methine as well as this methyl group. But this methyl group is having the 3 hydrogens. So the de-shielding would be little bit low for these 3 hydrogens when compared to this particular hydrogen. So this is the second downfield signal. That means you can say this signal is due to the presence of CH3 which is connected with the carbonyl group, right? You can see, right? And then next one is, you can say, this particular one. This is where beta carbon, and this is also the beta carbon, right? But this would be your third most downfield because the number is 2. You can say this is alpha, this is beta, this is alpha, this is also beta. So both these are beta, but you can see this beta carbon is having only 2 hydrogens. So the de-shielding effect will be higher on these 2 hydrogens when compared to these 3 hydrogens. So this would be your third most downfield signal. So I'm writing third most downfield signal. Third most downfield signal. It clearly indicates that these particular signals is due to the CH2 group. This typical pattern is due to this CH2 group, right? And you can see this would be your most upfield signal. This is where most upfield. Why most upfield? because it is very far away from this carbonyl group. So it will be very, very upfield. That means the highest, that means the lowest delta ppm, lowest value of the chemical shift will be present. That mean lowest value of the chemical shift would be there for this particular methyl group, and it will produce a triplet. So this CH3. So this signal A basically is belong to the this particular CH3, right? And then you left with this doublet. How we are getting this particular doublet? This doublet is due to this methyl group, right? So this methyl group which is connected with this one. Okay, so what we can do, we can straightforward connect this. Okay, this signal is due to this one, and this triplet is due to this one. I hope this is quite clear. Now we need to understand the splitting pattern of this CH2 group. This is very, very important, and this will give you the idea how we can interpret the NMR spectrum in the different way. Okay, so you can see here what I can do. I can write like this. Say this is my CH2 group, and this is connected with the CH here, and here it is connected with the CH3, right? And we are going to decide the splitting pattern of this one. So what will happen? This CH2 can couple with this hydrogen, right? And this can also couple with this hydrogens, right? But the question is that whenever these two different kinds of the sets of the hydrogens are there, and this CH2 is coupling with both of them, and with which actually this CH2 will couple first, this will be decided by the value of the coupling constant. You can very easily calculate the coupling constant from here to here. So if I calculate the coupling constant, say between these two peaks, right? Between these two peaks, I am calculating the coupling constant. So this value is your 472.77, and this particular value is 465.36. If you subtract this, then you will get 1. Similarly, in the second one, say for example, if you want to calculate the coupling constant, so you will take this particular value of 395.92, and this is the second coupling constant, which is your 388.98, right? So this will give you 4, and then 18 minus 9 is 9. Higher the value of the coupling constant, first it will couple with the another hydrogen, right? Since both the values are very close, approximately 7 hertz. Coupling constant for both of them is 7 hertz, but not exactly 7 hertz. If these two values are exactly 7 hertz, then definitely what will happen? You will get the quintet. Okay, say for example, this coupling constant and this coupling constant is having the identical value, so you will get a quintet. How quintet? 3 hydrogens are here, 1 hydrogen is here, so 3 plus 1, that is 4. Or if you apply the n plus 1 rule, n plus 1, that will give you 4 plus 1, and it will give you the 5, and this will be your quintet. But this is possible only when these two coupling constant are exactly same or the identical. They are not identical, but they are somewhat similar. So it means that you will not get quintet, you will get some other splitting pattern. So what is that other splitting pattern? We need to decide this thing. Okay, so I am telling you what is happening here. Actually, this particular CH2 will produce DQ. It will produce your DQ, and the full form of the DQ is doublet of quadrate. Why doublet of quadrate? I am telling you, the value of the coupling constant. Say for example, I can mark this, say this is my A, this is my B, this is my C. Okay, so this coupling constant is little bit higher. However, they have the roughly same value of the 7 hertz, but I'm telling you this value is little bit higher, right? So what will happen? This CH2 will couple with this hydrogen first. Since the neighboring hydrogen is only one, you will get a doublet here. What you will get? You will get a doublet. So I am drawing a doublet here. JAB. What I have written over there? JAB. What is the meaning of JAB? These A hydrogens are coupling with the B. So you are getting a doublet. This one. Now what will happen? Each of the peak of the doublet, that means these two peaks, right? This peak will couple with this methyl group, right? And then your second peak will also couple with this methyl group. Each peak will split into a quadrate. You are having these two peaks, which I have drawn, and then you see neighboring hydrogens are 3. So again you will apply n plus 1 rule. This will give you 3 plus 1, that is 4. That means each of them will now split into the two sets of the 4 peaks. You can draw like, and this is basically your JAC. Why JAC? Previously it was coupled with this one JAB. Now it is coupling with this one, that is JAC. Okay, and you are having this 1 2 3 4 5 6 7 8. This pattern you are having. I'm drawing the peaks here. So this will produce a pattern like that. One, they are quadrates. This is known as doublet of quadrates. So this CH2, right? This CH2 will produce a doublet of quadrate. So this particular region, right? This is basically the signal which is due to the presence of this CH2 group. Now in the expansion, I'm going to this particular expansion, right? You see this expansion which I have shown you here. I have shown you only 8 peaks, right? 1, 2, 3, 4, 5, 6, 7, 8. But here you can see the number of peaks are quite large. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Many peaks are there. You can see the complex splitting pattern. These lines we have calculated theoretically. So somehow we are very close to this particular pattern, but not exactly to this particular pattern. But this is the only possible way by which you can get this particular pattern of the peaks. Okay, there is no other way to get this particular pattern. Please remember. Okay. So now if I go back, this CH, why we are getting this peak? So if I go to the expansion of this one, so 1, 2, 3, 4, 5, 6. Total 6 peaks I am getting. So this is my CH3, CH, and then CH2. What I can do, I can mark it as, say this is my hydrogen A, and this is my hydrogen B, and this is my hydrogen C. Now again what you can do, say this CH can couple with this CH2, this can also couple with this CH3, but I am telling you this value of the CH when coupled with the CH3, this coupling constant is slightly higher than the coupling constant with this CH2. So basically this J value is little bit higher. So this hydrogen will couple first with this particular 3 hydrogens. So if you apply the n plus 1 rule, okay, for a splitting pattern of this one, 3 neighboring hydrogens plus 1 equals to 4. So this will produce a quadrate, right? This will produce a quadrate. So I am drawing your quadrate. This quadrate, each of the line or of the quadrate will couple with this CH2, and again you will apply the n plus 1 rule. So now the neighboring hydrogens are 2 connected with this one hydrogen. This will give you 3. So each of the peak will now split into the 3. So how many peaks I am getting? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 peaks basically we should get. How? I am drawing this 1, 2, but we are getting only these much of 6 lines or the 6 peaks. This is due to the overlapping of the peaks. This is due to the overlapping of peaks due to similar J values. Due to similar J values. Okay. This structure is more consistent with the data given in the IR spectrum, proton NMR spectrum, and as well as the splitting pattern, right? This is the best possible explanation for this particular molecule. So if you want, then you can decide the value of the carbon chemical shift as well. Say for this carbon, the value is 213 picometer. Okay. So this is most upfield signal. This is 16 ppm, right? And this one is the second most downfield signal after 213. So this will resonate at 49 ppm. Please remember, this is resonate at 49 ppm. Okay. And then this will resonate at 28 ppm. Okay. And then you are having this particular one. This will resonate at 26 ppm. And finally, sorry, not this one is not 16. This will resonate at 12 ppm. I'm sorry, 12 ppm, and this will resonate at 16 ppm. So this is how you can solve the typical problems with the help of the depth NMR data. Okay. From the chapter Combined Spectral Problems, and this question was actually asked by one of my subscriber who was struggling to solve or to get the correct answer for this particular question. So today, I am here with the solution of this particular question. What is the question? Determine the structures of the isomeric compounds A and B. You have been given two isomeric compounds A and B, each of which has the formula C8H7BRO, which I have written over there as well. The IR spectrum of compound A has a strong absorption band at 1698 centimeter inverse, while compound B has a strong band at 1688 centimeter inverse. The proton NMR spectrum for compound A is shown along with the expansions for the region from 7.7 to 7.2 ppm, and the expansion is on the next page. And the NMR spectrum of the compound B is also attached, which is on the third page. Okay. So I'll solve this problem according to my usual way. First of all, we'll calculate the hydrogen deficiency index, and it is for the beginners. However, it is clearly given here. You are getting a signal here at 7 ppm. It clearly indicates the presence of the benzene ring. Okay. And along with this kind of the multiplate, you are having only one peak. So spectrum is looking quite simple, but its expansion, the expansion of this particular region will give you the more insight about the structure. Okay. But as my usual way, first of all, I will calculate my hydrogen deficiency index. So here the formula is 2C plus 2 plus N minus H minus X over 2, where C is the number of the carbon atoms. So 2 times 8, right? And then plus 2, and then plus 0 because no nitrogen is present here, minus 7, which are the hydrogens, and then the minus 1 divided by 2. Minus 1 is for your one of the halogens, which is present here. And if you solve this value, then you will have this hydrogen deficiency index of 5. And this 5 basically indicates the combinations of the rings and the double bonds. Since I am having my proton NMR spectrum, which is giving a signal at 7 ppm, so one thing is clear, my molecule is having this particular benzene ring, right? So this benzene ring basically fits in the hydrogen deficiency index of 4 because 3 double bond and 1 ring is there. Okay. And now you left with the fifth hydrogen deficiency index, and of course it is basically your carbonyl group. So in this particular question, in the little while you will find that IR information which we'll get from the information which we are having from the IR spectrum is more important to solve this particular question. Okay. So first of all, it is showing two very strong absorption. Strong absorption means your polar group is present, and that polar group is the carbonyl group. Okay. And in the compound A, it is resonating at 1698 centimeter inverse, and in the compound B, it is resonating at 1688 centimeter inverse. That means little bit of lower frequency is there. That means to stretch this carbonyl bond, we will require the little bit lower energy for this particular compound B when compared to the compound A, because it is having this 1698 centimeter inverse of this frequency which is corresponding to the little bit of higher energy, right? So and then you are having this carbonyl group, and bromine is already there. So we can quickly discard the possibilities of having acids, because acids are having two oxygens which are not there in the question. Similarly, you can discard the possibility of the esters as well, okay, and other acid derivatives. So the only possibility you left with is the presence of the carbonyl group, either in the form of the ketone or in the form of the aldehyde. But aldehydic possibility we can safely discard, because your aldehyde proton resonates between 9 to 10 ppm. That means if this carbonyl group is of your aldehydic carbonyl group, then you must have a signal between 9 to 10 ppm in the proton NMR spectrum, which is absent here. So that means this compound is not aldehyde, it is simply a ketone, right? And you are having this singlet. Singlet, you know how we can get the singlet. Singlet we can get by this CH3. Okay. So, and these three fragments we have already identified. Now, last is your BR. So, basically, these are the four things which you need to put together in order to get the correct structure for this proton NMR spectrum. Okay. So, it's simply the acetophenone type of the compound in which your bromine is substituted. Okay. And when you substitute bromine on the acetophenone, it may be your ortho substitution, it may be your meta substitution, it may be your para substitution. Okay. But before going further, you need to check this particular expansion which is given on the next page. Okay. So this is the complete expansion, and it is very important for the students to know or to identify the pattern given in the expansion for the particular compound, right, in the proton NMR spectrum. So what I am observing here, it is very important thing. See, I am having one peak is here. This is one peak. Okay. I am writing one peak. Okay. And my second peak is this one. So this is your second peak. And my third peak is this one. So I am writing this is as third peak. And the last one is my fourth peak. That means in the proton NMR spectrum, you are getting 4 peak for benzene. Why benzene? Because it is the expansion of the benzene region, which is extending from 7.24 ppm to 7.64 ppm. So you can say how I am counting the only 4 peaks. However, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 peaks are there. No, they are not 11 peaks. They are the complex splitting pattern of the 4 peaks. When your benzene molecule is having 4 peaks, that means you are having the 4 different hydrogens. So how we can get the 4 different hydrogens? You have this benzene, and say your carbonyl group is here, CH3, and I am substituting my Br here. Okay, this is the one possibility. This is your ortho-bromo-acetophenone. So if you write this ortho isomer, then you will have this hydrogen, and you will have this hydrogen again, and you will have this hydrogen again, you will have this hydrogen again. And for all of 4 these hydrogens are different. So all these will show different peaks in the proton NMR spectrum in the region between 7.1 to 7.5 ppm or 7.7 ppm. Okay. So this is basically, say, this is peak 1, this is peak 2, this is peak 3, this is peak 4. Okay. Now, or I can mark these hydrogens as a different hydrogens. Say for example, this is your, say, principal functional group. This is carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, and carbon 6. Okay. So I'm calling this hydrogen as the hydrogen 3. Okay. And this hydrogen as a hydrogen 4, this as hydrogen 5, and this as hydrogen 6. Now you can see here the environment of this particular hydrogen 3 is the bromine on the right hand side, while on the left hand side the environment of this hydrogen is hydrogen, only hydrogen. Okay. So this hydrogen is basically different from this particular hydrogen, because the environment of this hydrogen is H5 and H3. So these two are different. Similarly, if you see this hydrogen, meta to this hydrogen, at the meta position to this hydrogen is carbonyl group, while meta to this hydrogen is this Br group. That means this is also different from this one. That's why I have marked this hydrogen as the different hydrogen as H5. Similarly, this hydrogen in the ortho position is having your acetone functionality, while this hydrogen is having the Br functionality. So all these hydrogens are different kind of the hydrogens. When they are the different types of the hydrogen, they will produce different peaks in the NMR spectrum. So you will get the 5 peaks in the proton NMR spectrum. Okay. Now, if you see the pattern, this pattern is known as the DD pattern. DD means doublet of doublet. So this is one doublet, this is yet another doublet, this is known as the doublet of doublet. Okay. And then this one is also your DD, doublet and doublet pattern. But here you can see 1, 2, 3. 3 peaks are clustering at the same value, right? So this is known as basically TD, triplet of doublet. That means doublet 3 times, 1, 2, 3, and all are the doublets. So it is TD. And the last one is also your TD, which is known as the triplet of doublet. Now the question comes, why we are getting the triplets of the doublet? So, if you want to explain this doublet and doublet of doublet and then this triplet of doublet, so how we can explain? See, this H3, okay, this H3 will couple with this H4, so it will produce a doublet, and then again it will couple with this one, so it will again produce a doublet. So the doublet of doublet, which I have shown here. But this H4 is forming a triplet of the doublet. Why? Because this hydrogen will couple with this hydrogen, producing one doublet, and then this will couple with this one, it will produce another doublet. So two doublets are there, and then this H4 will couple with this hydrogen as well, meta coupling. So another doublet, so three doublets, and then you are having this hydrogen. So one doublet will be produced by this H6, another doublet will be produced by H4, and another doublet will be produced by the H3. So ortho and meta both couplings are there. So this will also produce triplet of the doublet. So these two, H4 and H5, will produce a triplet of the doublet, while this will produce only doublet of doublet. So it is quite simple here, you can see. So basically your compound is looking like that it is orthobromoacetophenone, CH3. They will produce only one singlet. Okay. So if you want, then you can very simply write this is giving your TD, this is also giving your TD, and this is giving you DD, doublet of doublet, right? Now the question comes, what if we have this particular isomer? So this is also having the different hydrogens. This is H, this is second H, this is third H, this is fourth H, and they all are different. Say HA, HB, HC, HD. This can also produce the similar NMR pattern which is given in the question, and I'm saying that this is correlating with this orthoisomer. Why it is not correlating with this one? The answer comes from the IR spectroscopy, right? IR spectroscopy in this case is very important in order to decide the structure. So what will happen, you see, in the question itself, it is given that for this particular compound, the value of your IR stretching frequency is 1698 centimeter inverse for your carbonyl. Why this happens? You see, this Br and this COCH3, they are at the ortho positions to each other. What will happen? This bromine will create steric repulsion to this carbonyl group, and due to this steric repulsion, this carbonyl group will no longer remain in the plane of the benzene ring. So the very smooth resonance overlap would not be there for this carbonyl to this benzene ring, because it is out of the plane. Due to the steric repulsion, it will be pushed, this carbonyl group will be pushed outside of the plane of the benzene ring, and there is no very smooth overlap. And you know, the conjugation lowers the stretching frequency in the IR spectrum. But here in this case, that conjugation is not very smooth. This will require little bit of high energy to stretch this carbonyl bond, which will reflect in the higher value of your carbonyl stretching frequency 1698. while in case of the meta isomer, this carbonyl group will remain in the plane of the benzene ring. So there is a very smooth conjugation, extended conjugation between this carbonyl and the benzene ring, and this value will not be very high like in the earlier case in the orthoisomers 1698. It will be somewhere around here 1988 centimeter inverse. That's why I am saying that this particular compound A, the isomer A, is basically your this particular compound, which is your orthobromoacetophenone. This thing is very important for you. Okay. Now, if you go back, you see here, this is the cluster, and the expansion of the cluster I have explained to you. Then you are having this one singlet, and that one singlet is due to this CH3. This is how I am confirming that this compound is basically your orthobromoacetophenone. Now, if you move further, say this is your compound B. So what is there in the compound B? You are having one singlet, of course this is for CH3, and then you are having only two doublets. You are having only two doublets. That means it's simply saying that you are having two sets of the hydrogen. One set of hydrogen, and this is second set of hydrogen. Only two sets of hydrogens are there. That means out of four hydrogens, two forming one group and other two forming two groups. And this will happen only in case of this isomer, right? Say for example, this is your benzene ring, and this is your COCH3, and at the para position you are having this Br. Okay. Now you see this molecule is having the plane of symmetry, which is bisecting this benzene ring from this carbon Br bond to the carbonyl bond. So if I try to put this, so this is the, you see this is the plane of symmetry which is going in that manner. So when plane of symmetry is here, that means this particular hydrogen, which I am calling as Ha, is identical to this hydrogen, which is your Ha. Similarly, this hydrogen we can mark as Hb, and this is also Hb. So due to this plane of symmetry, these two hydrogens are equivalent. These two hydrogens are equivalent. Okay. So equivalent hydrogens do not split each other, but this Ha will be split by the Hb. Only one hydrogen is there, so this will produce a doublet. One doublet for this Ha set. So I am writing here. Similarly, another doublet. Okay, that's why only two peaks are here, and one peak is for this particular one. So second isomer is basically your para isomer. In this para isomer, there is a very smooth conjugation between the electrons of the benzene rings and this carbonyl group. So lesser energy will require to stretch this particular bond, which will reflect in its lower value in 1688 centimeter inverse. So basically these two isomers belong to the two different kinds of the acetophenones. One is orthoderivative and second is the paraderivative. So there is no possibility of meta isomer in this case. Okay.